Every day, millions of Cadbury dairy milk bars are crafted inside state-of-the-art factories, where advanced machinery and carefully refined techniques transform raw cocoa into the smooth, creamy chocolate people love. The creation of a Cadbury dairy milk bar begins long before the chocolate reaches the factory. It starts on cacao farms located in tropical regions near the equator, where the conditions are ideal for growing cacao trees. The trees require warm temperatures, high humidity, and consistent rainfall to produce the cacao pods that contain the beans essential for making chocolate. These pods grow directly from the branches and trunk of the tree, taking around 6 months to mature. Farmers carefully monitor the pods, waiting until they turn from green to yellow, orange, or deep red, indicating ripeness. Harvesting is a meticulous process, as improper handling can damage the delicate cacao tree. Skilled workers use sharp machetes to cut the ripe pods from the tree, ensuring that the branch is left intact so that future pods can develop. Once harvested, the cacao pods must be processed immediately to prevent spoilage. The first step involves cracking open the thick, leathery shells to reveal the beans inside, which are surrounded by a sweet, sticky pulp. Farmers often use wooden clubs or knives to split the pods, being careful not to damage the beans within. Each pod contains around 30 to 50 beans, and thousands of these are needed to produce a single chocolate bar. The extracted beans and pulp are then placed into large wooden fermentation boxes, which are arranged in stacks to allow for air circulation. Fermentation is a crucial step in the chocolate making process, as it develops the complex flavors that will later be enhanced during roasting. The beans are left to ferment for 5 to 8 days, during which time they undergo chemical changes that transform their taste. The natural yeasts in the pulp break down the sugars, generating heat and causing the temperature inside the fermentation boxes to rise. This heat triggers biochemical reactions within the beans, breaking down their natural bitterness and releasing the precursor compounds that will later give chocolate its distinctive aroma and flavor. To ensure even fermentation, workers turn the beans periodically, usually once a day. This helps to distribute heat and oxygen throughout the pile while allowing excess moisture to evaporate. During this time, the beans gradually darken in color and develop a rich, earthy aroma. Without proper fermentation, the beans would retain a raw, astringent taste, resulting in low-quality chocolate. After fermentation is complete, the beans must be dried to reduce their moisture content and prepare them for transport. Traditionally, drying is done by spreading the beans out on large wooden trays or concrete surfaces under the sun. The drying process can take anywhere from 5 to 7 days, depending on the weather conditions. Workers frequently rake the beans to ensure they dry evenly and prevent mold growth. If the climate is too humid or rainy, mechanical dryers may be used to speed up the process and maintain quality standards. Once fully dried, the cacao beans are carefully sorted to remove any defective or damaged ones before being packed into jute sacks for shipment. These sacks are transported from cacao-producing countries to chocolate manufacturing facilities worldwide, including those used by Cadbury. Upon arrival at the factory, the first step in the production process is cleaning. The beans are loaded onto conveyor belts and passed through a series of cleaning machines that remove dirt, dust, and any remaining plant material. This ensures that only the highest quality beans proceed to the next stage. After cleaning, the beans are roasted to further develop their flavor. The roasting process is highly controlled, with temperatures and durations carefully calibrated to achieve the desired taste profile. The exact roasting conditions vary depending on the type of chocolate being produced, but for Cadbury dairy milk, the beans are typically roasted at temperatures between 120 to 150 degrees Celsius for about 30 to 45 minutes. During roasting, the beans undergo the Maillard reaction, a chemical process that enhances their flavor and aroma by breaking down proteins and sugars. The heat also causes the thin outer shells of the beans to become brittle, making them easier to remove in the next step. Once roasting is complete, the beans are cooled and sent through a machine called a winnower. This machine cracks the beans open, separating the outer shells from the inner nibs. The shells are removed using powerful air jets, leaving behind the pure cacao nibs, which contain the essential cocoa solids and cocoa butter needed for chocolate production. The nibs are then ground into a thick, liquid paste known as cocoa mass or cocoa liquor. This process is done using industrial grinding machines that apply high pressure to break down the nibs into tiny particles. The resulting cocoa mass has a rich, intense chocolate flavor, but is still quite coarse in texture. At this stage, the cocoa mass can be further processed to extract cocoa butter, a key ingredient in chocolate making. The mass is placed into hydraulic presses, which apply immense pressure to separate the fat, cocoa butter, from the solid components, cocoa solids. The extracted cocoa butter is a pale yellow, creamy substance that gives chocolate its smooth and creamy mouthfeel. Meanwhile, the remaining cocoa solids are ground into a fine powder, which can be used for making cocoa powder or reintroduced into the chocolate mixture for added richness. For Cadbury Dairy Milk, the next crucial step is blending the cocoa mass with other key ingredients, sugar and milk powder. Unlike dark chocolate, which relies on cocoa solids as the primary component, dairy milk chocolate has a significant proportion of milk, giving it a distinctively creamy texture and flavor. Cadbury uses fresh milk in its production process rather than relying solely on milk powder, a method that differentiates its chocolate from many other brands. The fresh milk is collected from dairy farms and transported in refrigerated tankers to the factory, where it undergoes quality control checks to ensure purity and freshness. Upon arrival, the milk is pasteurized to eliminate harmful bacteria and then concentrated to reduce its water content. This is achieved through a process called vacuum evaporation, in which the milk is heated under reduced pressure to remove excess moisture while preserving its natural flavor. The concentrated milk is then mixed with sugar to form a sweetened milk mixture, which is later blended with the cocoa mass. This unique approach, known as the crumb process, involves heating the milk and sugar together before adding them to the chocolate mixture. This technique enhances the caramelized notes of the chocolate and contributes to Cadbury's signature flavor. Once the cocoa mass, milk, and sugar are combined, the mixture undergoes refining to achieve a smooth consistency. Industrial refining machines use heavy rollers to grind the chocolate mixture, reducing the particle size to an ultra-fine level. This step is essential for creating the smooth, velvety texture that defines Cadbury Dairy Milk. If the particles are too large, the chocolate will have a grainy, rough mouthfeel, so precision in refining is crucial. The refined chocolate mixture, now resembling a dry, powdery substance, is ready for the next stage, conching. Conching is a continuous mixing and aeration process that further develops the chocolate's flavor and texture. The mixture is placed into large conching machines, where it is continuously stirred and heated for several hours. The duration of conching varies depending on the desired final texture and flavor, but for Cadbury Dairy Milk, it typically lasts between 4 to 6 hours. During this process, the chocolate's acidity and bitterness are reduced, while the smoothness and richness are enhanced. The heat and friction generated during conching also help to distribute the cocoa butter evenly, ensuring that the chocolate has a uniform texture. Once the conching process has refined the chocolate mixture into a smooth and well-developed liquid, it must undergo a crucial process known as tempering. Tempering is an essential step in chocolate production that ensures the final chocolate bars have a glossy finish, a firm structure, and the characteristic snap when broken. This process involves carefully controlling the temperature of the chocolate to stabilize the cocoa butter crystals. Cocoa butter exists in multiple crystalline forms, but only one of them, the beta crystal structure, provides the ideal texture and appearance for chocolate bars. If the chocolate is not tempered correctly, it can develop an unattractive, dull, or streaky surface and a grainy texture. Tempering is achieved through a series of precise temperature adjustments. First, the liquid chocolate is gradually cooled to around 27 to 28 degrees Celsius, which encourages the formation of stable beta crystals. Then, the temperature is raised slightly to about 31 to 32 degrees Celsius for milk chocolate, melting any unwanted crystal structures while keeping the stable ones intact. This ensures that when the chocolate cools and solidifies in the molds, it will have a smooth and uniform consistency. Large-scale chocolate tempering machines, which are fully automated, are used in Cadbury's factories to maintain this process with extreme precision. These machines continuously agitate the chocolate while controlling its temperature at various stages, ensuring that the cocoa butter crystallizes correctly. Once tempering is complete, the chocolate is ready for molding. The tempered chocolate is transferred to an automated molding system where it is poured into specially designed molds that give Cadbury dairy milk bars their iconic shape and thickness. The molds are made of food-grade polycarbonate plastic or stainless steel and are designed to create perfectly uniform chocolate bars. The molding system ensures that each bar receives the precise amount of liquid chocolate needed for consistent weight and shape. To ensure that the chocolate fills every crevice of the mold and eliminates any trapped air bubbles, the molds pass through a vibrating station. This high-frequency vibration gently shakes the molds, allowing the liquid chocolate to settle evenly and remove any unwanted air pockets. This step is crucial in creating a uniform texture throughout the bar, as any trapped air can lead to weak spots or inconsistencies in the final product. Once the chocolate is evenly distributed in the molds, the bars must be cooled to solidify completely. The molds move along a conveyor belt into a cooling tunnel, a temperature-controlled environment that gradually reduces the temperature of the chocolate. Cooling must be done gradually to prevent the formation of sugar or fat bloom, which can create a white or grayish appearance on the surface of the chocolate. The cooling tunnels are typically set at temperatures between 5 to 10 degrees Celsius, and the bars spend around 20-30 minutes inside, depending on their thickness and size. During this time, the chocolate transitions from a liquid state to a solid form with a firm structure and smooth texture. After cooling, the solidified chocolate bars are carefully removed from the molds using an automated demolding system. This process is designed to be gentle to prevent breakage, ensuring that each bar maintains its perfect shape. The bars are then sent along conveyor belts for the next stage, quality inspection. At this point, every chocolate bar undergoes a thorough quality control check to ensure it meets Cadbury's strict standards. High-speed cameras and laser sensors scan the chocolate bars for any imperfections, such as cracks, air bubbles, or irregular shapes. Bars that do not meet quality standards are removed from the production line and either reprocessed or discarded. Factory workers also conduct random manual inspections, checking for surface smoothness, uniform thickness, and the signature Cadbury dairy milk texture. Once the bars have passed the quality inspection stage, they move on to the packaging process. Packaging is an essential part of chocolate production, as it protects the chocolate from external factors such as moisture, air, and temperature changes that could affect its quality. The packaging process begins with automated machines wrapping each chocolate bar in a protective layer. Traditionally, Cadbury dairy milk bars were wrapped in foil with a paper sleeve, but modern packaging now consists of a specially designed plastic film that provides better sealing and protection. The packaging machines work at incredibly high speeds, wrapping hundreds of chocolate bars per minute. Each bar is precisely aligned and fed into the packaging machine, where the plastic film is cut and wrapped tightly around it. Heat sealing technology ensures that the package is securely sealed, keeping the chocolate fresh and protected from environmental factors. Once wrapped, the bars are sent through a labeling station, where product information such as batch numbers, expiration dates, and barcodes are printed onto the packaging. After labeling, the individually wrapped chocolate bars are grouped together into larger multi-packs or cartons, depending on the intended retail format. These multi-packs are then placed into shipping boxes, which are sealed and prepared for distribution. To ensure efficiency in the supply chain, Cadbury's factory uses automated robotic systems to stack the finished boxes onto pallets. These robotic arms work with incredible precision, organizing the boxes in a way that maximizes space while ensuring stability during transport. The pallets of Cadbury Dairy Milk bars are then transferred to the factory's storage and distribution center, where they are kept in temperature-controlled warehouses before being shipped to retailers worldwide. The storage conditions are carefully maintained to prevent temperature fluctuations, as chocolate is highly sensitive to heat and humidity. Ideal storage temperatures for chocolate typically range between 15 to 18 degrees Celsius to prevent melting, fat bloom, or sugar crystallization. Once ready for distribution, the chocolate bars are loaded onto refrigerated trucks and transported to supermarkets, convenience stores, and other retail outlets. Cadbury ensures that strict logistics and transportation protocols are followed to maintain the quality of the chocolate during transit. These trucks are equipped with temperature-controlled systems that prevent overheating or exposure to extreme temperatures, ensuring that the chocolate arrives in perfect condition. Upon arrival at retail locations, the chocolate bars are displayed on store shelves, ready for consumers to purchase. The iconic purple packaging and recognizable branding make Cadbury Dairy Milk one of the most easily identifiable chocolate products on the market. From the initial stages of cacao cultivation to the moment a customer unwraps a bar, every step in the production process is meticulously designed to deliver the perfect balance of smoothness, creaminess, and rich chocolate flavor that has made Cadbury Dairy Milk a favorite for generations. The next stage in the manufacturing process is focused on large-scale efficiency, ensuring that every single Cadbury Dairy Milk bar produced maintains the same level of quality, texture, and taste. Once the bars are molded, cooled, and packaged, the production line moves seamlessly into the next critical phase: quality control and inspection. While some initial checks were already performed during molding and packaging, this stage is dedicated to an in-depth analysis of every batch to guarantee consistency. Cadbury employs an extensive quality control system using a combination of automated technology and human oversight. High-speed cameras and infrared scanners are positioned along the conveyor belts to detect any visible imperfections, such as cracks, surface defects, or uneven molding. These sophisticated imaging systems compare each chocolate bar against a pre-programmed reference model, instantly flagging any inconsistencies. Defective bars are automatically removed from the production line and sent to a separate area where they may be either reprocessed or discarded depending on the severity of the defect. Beyond the physical appearance of the bars, texture and taste are also key factors that must be evaluated. Every production batch undergoes sample testing, where factory workers manually inspect a random selection of bars, breaking them to listen for the characteristic snap that signifies proper tempering. The texture is also analyzed using precision measuring instruments that evaluate the chocolate's density and uniformity. To maintain Cadbury's signature creamy mouthfeel, particle size analysis is conducted to ensure that the chocolate's refined mixture maintains a smooth consistency. If any deviations are detected, the production settings are adjusted in real time to correct potential issues before they impact the entire batch. In addition to visual and textural inspections, extensive taste testing is performed. Cadbury employs trained sensory panels, experts with highly developed palates, to sample and evaluate each batch of dairy milk chocolate. These professionals assess the chocolate for its signature balance of sweetness, creaminess, and cocoa richness. The sensory panelists follow a structured evaluation process examining attributes such as melt rate, lingering aftertaste, and flavor complexity. To ensure objective results, the tasters follow strict guidelines, such as cleansing their palates between samples and tasting in a controlled environment, free from external odors or distractions. Once the quality control stage is successfully completed, the chocolate bars proceed to the final stage of distribution. At this point, thousands of bars are packed into cartons and prepared for shipment. The logistics of distributing Cadbury Dairy Milk bars to retailers worldwide is a highly coordinated effort. Each carton is scanned, labeled, and sorted based on its destination. Advanced inventory management systems track every unit in real time, ensuring that supply chain operations remain smooth and efficient. Temperature-controlled storage is an essential part of this process. Since chocolate is highly sensitive to temperature and humidity, Cadbury warehouses maintain precise environmental conditions. Storage temperatures are carefully kept within the optimal range of 15 to 18 degrees Celsius to prevent issues such as fat bloom, a white discoloration caused by fat migration, or sugar bloom, a grainy surface texture caused by moisture exposure. To further protect the chocolate, humidity levels in the warehouse are monitored to prevent condensation from forming inside the packaging. Once the chocolate bars are ready for transport, they are loaded onto specially designed delivery trucks equipped with temperature regulation systems. These vehicles are programmed to maintain ideal conditions throughout transit, ensuring that the chocolate does not melt or suffer quality degradation. The bars are then transported to distribution centers, where they are sorted and prepared for delivery to supermarkets, convenience stores, and online retailers. The final stage of the Cadbury Dairy Milk Bar's journey, from its creation in the factory to reaching the hands of consumers, is a combination of advanced logistics, careful storage, and precise distribution. Ensuring that millions of chocolate bars arrive in perfect condition across the globe requires an intricate supply chain. Every Cadbury Dairy Milk bar, once fully manufactured, undergoes a detailed process of warehousing, transportation, retail placement, and eventual purchase by consumers. After passing rigorous quality control checks, the packaged chocolate bars are sent to Cadbury's automated warehousing facilities. These warehouses are designed with climate control systems that maintain optimal conditions for chocolate storage. Chocolate is highly sensitive to temperature fluctuations and humidity, which can lead to fat bloom or sugar bloom if not stored correctly. Fat bloom appears as a whitish discoloration on the chocolate surface, caused by unstable cocoa butter rising to the surface when exposed to inconsistent temperatures. Sugar bloom, on the other hand, results from moisture interacting with sugar particles, causing a rough and grainy texture. To prevent these defects, Cadbury's warehouses maintain a consistent temperature range of 15 to 18 degrees Celsius and humidity levels below 50%. Within the warehouse, an automated storage and retrieval system organizes and categorizes the chocolate bars based on their batch numbers and expiration dates. These systems use robotic arms and conveyor systems to efficiently stack and move cartons of dairy milk bars without human intervention, ensuring minimal handling and reducing the risk of damage. Advanced barcode and RFID scanning technology is employed to track every individual batch, allowing real-time monitoring of inventory levels. This ensures that products are shipped in the correct order, prioritizing freshness and reducing waste. Once ready for distribution, the Cadbury Dairy Milk bars are loaded onto transport trucks for delivery. The logistics of transporting chocolate require carefully planned routes and specially equipped vehicles to prevent exposure to extreme temperatures. In warmer climates, refrigerated trucks are used to maintain the optimal temperature during transport. These trucks are fitted with sensors that continuously monitor temperature conditions, ensuring that any fluctuations can be corrected before they affect the product's quality. From the warehouse, the chocolate bars are delivered to national and international distribution centers. These hubs play a crucial role in breaking down large shipments into smaller deliveries destined for specific retailers. Here, logistics teams coordinate the efficient redistribution of the products to supermarkets, convenience stores, online retailers, and vending machine suppliers. The entire process is optimized using software systems that calculate the most efficient routes and delivery schedules, reducing transit time and ensuring the freshest product reaches store shelves as quickly as possible. Upon arriving at retail locations, Cadbury dairy milk bars are placed in designated areas based on carefully planned merchandising strategies. Retailers follow specific guidelines to position the chocolate bars in high-traffic areas, maximizing visibility and impulse purchases. Supermarkets often stock dairy milk bars in checkout aisles, where customers are more likely to grab a bar as a last-minute addition to their purchases. Convenience stores and gas stations also follow similar placement strategies, ensuring that dairy milk bars are easily accessible and prominently displayed. Beyond traditional retail spaces, online shopping has become an increasingly important channel for Cadbury dairy milk sales. E-commerce platforms allow consumers to order chocolate bars directly from Cadbury or through third-party retailers. These online orders are fulfilled from dedicated warehouses where products are carefully packed to prevent breakage during shipping. Insulated packaging may be used in regions with hot climates to ensure that the chocolate remains solid during transit. Subscription services and bulk purchasing options also contribute to the growing presence of dairy milk in the online marketplace. Once the chocolate bar reaches the hands of the consumer, the experience of enjoying Cadbury dairy milk is the culmination of a long and carefully controlled process. The signature smooth texture and rich taste of the chocolate are as a result of every meticulous step taken throughout the journey, from the cacao farms to the final packaging. The unique flavor of dairy milk is achieved through the combination of high-quality cocoa beans, fresh milk, and precisely controlled manufacturing techniques. In addition to producing high-quality chocolate, Cadbury is also committed to sustainability and ethical sourcing. The company's partnership with the Cocoa Life program ensures that the cocoa used in dairy milk bars is sourced responsibly. This initiative works directly with cocoa farmers to improve farming practices, provide fair wages, and promote environmental conservation. By investing in sustainable cocoa production, Cadbury helps to support the livelihoods of farmers while ensuring a stable and high-quality supply of cocoa for the future. Similarly, Cadbury has made strides in reducing its environmental footprint in manufacturing and packaging. The company is working towards more sustainable packaging solutions, aiming to reduce plastic waste and increase recyclability. Innovations such as thinner plastic film, recyclable paper-based wrappers, and biodegradable packaging materials are being developed to align with global sustainability goals. In the manufacturing process, energy-efficient machinery and waste reduction programs contribute to minimizing the factory's carbon footprint. The journey of M&M's production begins long before the candies take their familiar shape. It all starts with sourcing the finest raw ingredients, ensuring that only the highest quality materials make their way into the manufacturing process. The primary component of M&M's is chocolate, which requires premium cocoa beans. These beans are cultivated in tropical regions across the globe, primarily in West Africa, South America, and parts of Southeast Asia. The selection of cocoa beans is an extremely meticulous process, as the quality of the beans directly impacts the flavor and texture of the final product. Once the cocoa beans are harvested, they are fermented to develop their rich chocolate flavor. This is a crucial step that involves placing the freshly gathered beans in wooden boxes or spreading them out on banana leaves, where they are covered and left to ferment for several days. During fermentation, the beans undergo chemical changes triggered by naturally occurring bacteria and yeast. This process reduces the beans' natural bitterness and enhances the complexity of their flavor profile. Regular stirring and aeration ensure even fermentation, and expert cocoa farmers Monitor the process closely to prevent over-fermentation, which could compromise the beans' quality. After fermentation, the beans are dried under the sun, further intensifying their chocolatey aroma. The drying process can take several days and must be carefully managed to prevent mold growth. The dried beans are then packed into large sacks and shipped to chocolate manufacturers, including those that supply chocolate for M&M's production. Once the cocoa beans arrive at the processing facility, they undergo rigorous quality control checks. Samples are taken from each shipment to assess various characteristics such as bean size, moisture content, and aroma. Any beans that fail to meet the strict standards are discarded or repurposed. The approved beans then move on to the cleaning phase, where they pass through specialized machines equipped with powerful air jets, sieves, and magnets to remove unwanted debris such as dust, stones, and plant matter. The thorough cleaning ensures that only pure cocoa beans proceed to the next stage of the process. With the beans cleaned and sorted, the next step is roasting, a critical phase that brings out the rich, deep flavors of chocolate. The roasting process is highly controlled and varies depending on the desired flavor profile. Beans are placed into large rotating drum roasters, where they are exposed to carefully calibrated heat, typically ranging from 250 to 350 degrees Fahrenheit. The length of roasting time can vary from 30 minutes to over an hour, depending on the type of chocolate being produced. As the beans roast, the heat triggers complex chemical reactions, including Maillard reactions and caramelization, which contribute to the depth and complexity of the chocolate flavor. Roasting is not just about flavor. It also helps loosen the thin outer shell of the cocoa bean, making it easier to separate the nibs, the inner, edible part of the bean, from the husk. Once roasting is complete, the beans are cooled rapidly to halt further cooking. They then move to the winnowing stage, where they are cracked open, and the husks are separated from the nibs using a combination of sieving and airflow. The husks, now removed, are often repurposed for agricultural use or discarded. Now it's time to transform the roasted nibs into a smooth, rich chocolate base. The nibs are passed through heavy-duty grinding machines, where they are ground down into a thick liquid paste known as cocoa mass or cocoa liquor. This grinding process generates heat, causing the natural cocoa butter within the nibs to melt and blend with the cocoa solids. The result is a velvety, rich substance that serves as the foundation for all chocolate products, including the chocolate cores of M&Ms. At this stage, the cocoa mass is still quite bitter and lacks the smoothness associated with high-quality milk chocolate. To refine its texture and taste, it is mixed with additional ingredients, including sugar, milk powder for milk chocolate varieties, and more cocoa butter. The exact proportions are carefully controlled to ensure consistency across every batch. The blended mixture is then sent through refining rollers, which grind the chocolate particles to an incredibly fine texture, reducing them to just a few microns in size. This refining step is crucial for ensuring the signature smoothness of M&M's chocolate. But up next, the chocolate must undergo a crucial process known as conching. Conching is an intensive mixing and aeration process that enhances both the texture and flavor of the chocolate. Large, specialized machines equipped with rotating paddles continuously churn the chocolate mixture for several hours, or even days, depending on the manufacturer's specifications. During conching, heat and friction help to evaporate unwanted volatile acids, mellowing the chocolate's flavor and reducing any residual bitterness. This step also ensures that the chocolate reaches an exceptionally fine and uniform consistency, eliminating any remaining graininess. Once conching is complete, the chocolate must be tempered, a carefully controlled process that ensures the chocolate has a stable crystalline structure. Tempering involves heating the chocolate to a precise temperature, cooling it slightly, and then reheating it to another specific temperature. This controlled cooling and reheating process encourages the formation of stable cocoa butter crystals, which give M&M's chocolate centers their signature snap and glossy finish. If chocolate is not properly tempered, it can develop a dull, chalky appearance and an undesirable, crumbly texture. With the chocolate now perfectly tempered, the next step is forming the small, round chocolate cores that will become the centers of M&Ms. The tempered chocolate is dispensed into specially designed molding equipment that shapes the chocolate into tiny, uniform spheres. These chocolate pieces are rapidly cooled to solidify their structure, ensuring they maintain their perfect shape. Once solidified, the chocolate centers are ready for the next stage of production. But before the chocolate centers can move on to the next phase, they undergo another round of quality control. Sophisticated scanning and sorting machines inspect each individual piece for size, shape, and texture consistency. Any chocolate pieces that do not meet the exact specifications are removed from the production line and either reprocessed or discarded. At this point, the chocolate cores are complete, but they are still missing the signature crunchy sugar shell that makes M&Ms so iconic. To prepare for the coating process, the chocolate pieces are carefully transferred to large rotating drum machines where they will be transformed into the colorful candies known around the world. Now it's time to begin the intricate process of coating the chocolate centers with their signature sugar shell. The process starts with a sugar syrup mixture made from granulated sugar and water, which is heated to an exact temperature to achieve the correct viscosity. The sugar syrup is prepared in carefully monitored mixing tanks to ensure consistency across every batch. Once the sugar syrup is ready, the chocolate cores are placed into large rotating coating pans. These specialized pans are designed to gently tumble the chocolate centers, allowing for even application of the sugar coating. The sugar syrup is added in small increments, gradually building up the shell layer by layer. After each application, the candies are briefly dried using controlled airflow to harden the sugar coating before the next layer is applied. This step is repeated multiple times, as the sugar shell must reach the perfect thickness to provide the signature crunch that M&Ms are known for. Throughout the coating process, precise measurements are taken to ensure each M&M receives an even and consistent sugar shell. The candies are inspected at multiple stages to verify their size, shell thickness, and overall quality. Any irregularly shaped pieces are removed to maintain the brand's strict standards. Now it's time to explore one of the most intricate and carefully controlled stages of the M&M's manufacturing process: the creation of the colorful sugar shell. This step is essential as it gives M&Ms their signature crunch, vibrant appearance, and prevents the chocolate core from melting in consumers' hands. The process of coating the chocolate centers in sugar is not a simple one. It requires multiple layers of application, precise drying techniques, and exacting quality control measures to ensure that each candy turns out perfectly. The process begins with preparing the sugar syrup, which serves as the base for the outer shell. This syrup is made by dissolving high-quality granulated sugar in water and heating it to an exact temperature to achieve the desired consistency. The proportions of sugar and water must be carefully controlled to ensure that the final coating will be thick enough to provide a satisfying crunch while remaining thin enough to allow for a smooth, even color application later in the process. Large industrial mixing tanks continuously stir the solution to maintain uniformity, preventing sugar crystals from forming prematurely, which could create an undesirable, grainy texture in the shell. Once the sugar syrup is prepared, the chocolate centers that have been formed and cooled in the previous step are placed into massive rotating coating pans. These pans, also known as dragee pans, are large, circular drums that spin at a carefully controlled speed, allowing the candies to tumble evenly as the sugar syrup is applied. The process of coating the chocolate centers in sugar is known as panning, and it is a delicate operation requiring expert control over temperature, humidity, and airflow. The first application of sugar syrup is extremely light, providing only a thin base layer that helps the subsequent layers adhere properly. After each addition of syrup, a controlled airflow is introduced to the rotating pan to help dry the layer and prevent the candies from clumping together. The drying step is just as critical as the application itself. If the sugar syrup remains too wet for too long, it can result in an uneven coating or cause pieces to stick together, leading to misshapen M&Ms. This layering process is repeated multiple times, gradually building up the shell to its final thickness. Each new layer of syrup must be carefully measured and evenly distributed across all the candies in the pan to ensure a uniform shell thickness. The factory uses automated sensors to continuously monitor the weight and diameter of the candies, ensuring that each M&M receives the same precise amount of coating. If any inconsistencies are detected, adjustments are made in real time to correct the issue. The drying process also plays a key role in determining the final texture of the shell. Factories use sophisticated drying chambers that regulate temperature and humidity with extreme precision. The drying process must strike a perfect balance. Too much heat too quickly can cause the sugar to crystallize unevenly, leading to a rough texture, while too little heat can leave the shell sticky and prone to damage. Airflow systems within the factory ensure that the drying process occurs gradually and consistently across every batch. The next challenge in the sugar coating stage is ensuring that the candies remain perfectly spherical as the layers build up. If the panning speed is too high or the syrup is applied unevenly, the candies can develop a slightly oblong or irregular shape. To prevent this, highly skilled operators oversee the process, adjusting pan rotation speeds and syrup application rates as needed. The use of vibration sensors and laser scanning technology further helps detect any irregularities in shape, allowing for real-time corrections. Throughout this process, thousands of tiny M&Ms are tumbling together in the massive coating pans, yet they must all maintain a uniform appearance and size. To achieve this, the factory employs a combination of mechanical precision and human oversight, ensuring that every step of the sugar coating process adheres to the highest quality standards. This level of detail and control ensures that every M&M that makes it into a package is identical in texture, thickness, and size. But up next, now that the sugar shells have reached the correct thickness, it's time to introduce the vibrant colors that make M&Ms so instantly recognizable. However, before any color is applied, the candies are still a plain white or light beige color, lacking the bright and varied hues that consumers expect. The process of adding color is just as intricate as the coating process itself, requiring precise dye applications, careful drying, and rigorous quality control checks. The first step in coloring M&Ms is preparing the food-safe dye solutions. Each color, red, yellow, blue, green, orange, and brown, is created using a carefully controlled blend of FDA-approved food colorants mixed with water and a small amount of sugar. The color solutions are stored in separate stainless steel tanks, each dedicated to a single hue, ensuring that no cross-contamination occurs. These solutions must be continuously stirred to maintain an even distribution of the dye particles, preventing any inconsistencies that could lead to color variations in the final product. The M&Ms are then divided into different batches, with each batch destined to receive a specific color. The candies are transferred back into the rotating coating pans where the coloring process begins. Rather than applying the dye all at once, it is carefully sprayed onto the candies in multiple ultra-thin layers, allowing the color to gradually build up. This layering technique prevents the formation of streaks or uneven patches, ensuring a flawless and uniform appearance. The rotation of the pans ensures that every candy receives an even coat of dye, but this process must be monitored closely to prevent oversaturation, which could lead to color bleeding or an overly thick coating. The amount of dye applied is measured with extreme precision, and factory technicians continuously test samples to confirm that the color matches the exact shade required by the brand's strict specifications. If even the slightest variation in hue is detected, adjustments are made immediately to correct the issue before the batch proceeds further. After each layer of color is applied, the candies undergo another round of controlled drying. The drying process at this stage is particularly important because it ensures that the color sets properly without smudging or transferring onto other candies. A carefully balanced combination of warm air and controlled humidity is used to dry the candies gently, preserving the integrity of the color while maintaining the smooth texture of the shell. Once the final layers of color have been applied and the candies have fully dried, the next step is polishing, which gives M&Ms their signature glossy sheen. The polishing process involves adding a small amount of food-grade glaze, such as confectioner's glaze or carnauba wax, to the coating pans. As the pans rotate, the candies rub against each other, naturally buffing their surfaces to create a smooth, reflective finish. This step not only enhances the visual appeal of M&Ms, but also serves a functional purpose. It prevents the candies from sticking together during packaging and transportation. Now that the M&Ms have their final color and shine, they must go through one of the most iconic steps in the entire production process: the printing of the signature M on each piece. But before the candies can be stamped, they must be carefully arranged so that each one is properly oriented for printing. High-speed conveyor belts and automated sorting systems position the candies with their flattest surface facing upward, ensuring a consistent print placement. The printing process itself uses an advanced offset printing technique, which allows for rapid and precise application of the white M logo. A specially formulated food-grade white ink, made primarily from titanium dioxide, is applied to a flexible printing pad, which then transfers the design onto each individual candy. The pressure of the printing pad is carefully calibrated to ensure that the ink adheres without smudging or distorting the logo. But this process is not without its challenges. Each M&M must receive a perfectly centered M that is clear and consistent in size. High-speed cameras monitor the printing process in real time, scanning each candy to detect any misaligned or incomplete prints. If a candy does not meet the strict printing standards, it is automatically removed from the production line. This ensures that every M&M that reaches consumers is perfectly branded with the recognizable M logo. With the printing process complete, the M&Ms now have their final appearance, but they must still undergo rigorous quality control inspections to ensure they meet every specification before packaging. This final inspection phase uses advanced laser scanners, weight sensors, and visual inspection technology to detect any defects, such as size inconsistencies, color variations, or improper printing. Any candies that do not meet the standards are removed and either reprocessed or discarded. Now that the M&Ms have their final color, shine, and the iconic M printed on each piece, it's time to move into the packaging stage. Packaging is one of the most important steps in the entire process because it ensures the candies remain fresh, protected, and properly portioned for consumers. The packaging process must be extremely precise, as millions of M&Ms are produced daily, and each bag must contain the exact amount of product while maintaining the highest quality standards. The first step in the packaging process is sorting and portioning. The freshly finished M&Ms are transported from the production area to the packaging lines using specialized conveyor systems designed to prevent damage to the candies. These conveyor belts move the M&Ms in a controlled manner, preventing excessive friction or sudden impacts that could cause the candies to crack or chip. Before the candies reach the filling machines, they must be properly mixed to ensure an even distribution of colors in each package. To achieve this, large rotating drums mix the M&Ms together, creating a balanced blend of all the different colors. This step is crucial because consumers expect a diverse mix of colors in every bag, and any imbalances could lead to dissatisfaction. Sensors continuously monitor the mixture to ensure that no single color is overrepresented or missing from a batch. Once the M&Ms are thoroughly mixed, they move on to high-speed weighing machines that measure out exact portions. These machines use advanced load cell technology to ensure that each package receives the correct weight of product, whether it's a small single-serving bag or a large bulk container. If the weight of a portion does not fall within the acceptable range, the machine automatically adjusts the portion size or rejects the package, ensuring that every bag contains the precise amount of candy. After portioning, the M&Ms are funneled into packaging machines that fill them into different types of containers. The most common packaging formats include small plastic pouches, resealable bags, large family-size packs, and rigid plastic tubes. Each packaging type requires a different filling technique. For flexible bags, the M&Ms are dropped into pre-formed pouches, which are then sealed using heat and pressure to create an airtight closure. For rigid containers, such as tubes or bulk dispensers, the candies are carefully dispensed in controlled amounts to prevent breakage. One of the most critical aspects of the packaging process is sealing. The packaging must create an airtight barrier that protects the M&Ms from moisture, air, and temperature fluctuations, all of which could compromise their texture and flavor. Heat sealing technology is used for pouches and bags, ensuring a strong, tamper-proof closure. For resealable bags, a zipper-style closure is incorporated into the design, allowing consumers to open and close the package without compromising freshness. Each package is then labeled with important product information, including the expiration date, batch number, and barcode. These labels are applied with high-speed printing systems that ensure clear, legible text. The batch number is particularly important because it allows for traceability in case of any quality control issues. If a problem is detected in a particular batch of M&Ms, manufacturers can quickly identify and recall affected products using this tracking system. Before the packaged M&Ms are sent out for distribution, they must pass through a final quality control checkpoint. This stage involves multiple inspection systems designed to detect any defects or contaminants. X-ray machines scan the sealed packages for any foreign objects, such as metal fragments or plastic particles, ensuring the highest level of food safety. Optical scanners verify that each package contains the correct mix of colors and that there are no visual defects in the candies. Weight-checking systems also perform one last verification to ensure that every package falls within the acceptable weight range. If any package is found to be underfilled or overfilled, it is automatically rejected and sent back for reprocessing. This level of precision is essential for maintaining consistency across all M&M's products. Once the M&Ms pass the final quality control checks, they are grouped together and packed into larger cartons for distribution. The individual packages are stacked inside shipping boxes in a way that maximizes space efficiency and prevents movement during transportation. These cartons are then sealed and labeled with shipping information, including the destination, lot number, and handling instructions. Now that the M&Ms are packaged and ready to go, the next step is distribution. The packaged candies are loaded onto pallets and transported to regional distribution centers, where they are sorted based on their final destinations. From these distribution centers, the M&Ms are shipped to retail stores, vending machine suppliers, and online fulfillment centers. The logistics of M&M's distribution are highly optimized to ensure that products reach consumers as quickly and efficiently as possible. Temperature-controlled storage facilities are used to prevent the candies from melting or degrading during transit. This is particularly important in warmer climates, where exposure to high temperatures could cause the chocolate cores to soften and the sugar shells to become sticky. To maintain freshness and ensure a long shelf life, M&Ms are stored in climate-controlled warehouses before reaching store shelves. The shelf life of M&Ms can be up to 12 months, thanks to the airtight packaging and stable sugar shell that protects the chocolate from external factors. Retailers follow strict inventory rotation policies to ensure that the oldest stock is sold first, preventing any expired products from reaching consumers. Once the M&Ms arrive at retail locations, they are displayed in strategically placed sections of stores to maximize visibility and sales. The packaging design plays a key role in attracting consumers with bright colors and clear branding, making M&Ms easily recognizable on store shelves. In addition to traditional retail stores, M&Ms are also sold through vending machines, online retailers, and specialty candy shops. While the journey from raw cocoa beans to finished M&Ms is highly complex, the end result is a candy that is loved by millions of people around the world. The precision, technology, and craftsmanship involved in every step of the manufacturing process ensure that each M&M meets the highest standards of quality and consistency. But the innovation doesn't stop there. M&M's production continues to evolve with advancements in automation, sustainability initiatives, and new product development. For example, Mars, the company behind M&M's, has invested in sustainable cocoa sourcing programs to ensure that the chocolate used in their products is ethically and responsibly sourced. They are also working on reducing the environmental impact of their packaging by exploring recyclable and biodegradable materials. Additionally, new flavors and limited edition M&M's varieties are constantly being developed, requiring modifications to the production process. Whether it's peanut butter-filled M&M's, crispy rice varieties, or seasonal flavors, the core manufacturing process remains the same. But new ingredients and formulations require precise adjustments to maintain the signature M&M's experience. The continuous pursuit of quality and innovation is what has made M&M's one of the most enduring and beloved candies in the world. Every bag, from the smallest single-serving pouch to the largest party-sized container, goes through the same rigorous process to ensure that it meets the expectations of consumers. The creation of Reese's Peanut Butter Cups is a meticulous process that begins with the careful selection and preparation of peanuts, the cornerstone of the product's distinctive flavor and texture. This journey starts with sourcing high-quality peanuts, primarily from regions renowned for their optimal growing conditions, such as Georgia and Texas. These areas provide the ideal climate and soil composition, resulting in peanuts with the desired size, flavor, and oil content essential for the signature Reese's taste. Upon arrival at the manufacturing facility, the peanuts are subjected to a rigorous inspection process. Advanced optical sorting machines, equipped with high-resolution cameras and sensors, meticulously scan each peanut, identifying and removing any that are discolored, misshapen, or contaminated with foreign materials. This ensures that only the finest peanuts proceed to the next stage, maintaining the high-quality standards synonymous with Reese's products. Following sorting, the peanuts undergo a thorough cleaning process. They are funneled through a series of air classifiers and vibrating screens that effectively remove dirt, stones, and other debris. Some facilities may also employ water baths or steam cleaning methods to ensure an even higher level of cleanliness. This step is crucial, as any residual impurities could adversely affect the flavor and safety of the final product. The next phase involves roasting the cleaned peanuts to develop their rich, nutty flavor and achieve the desired texture. Industrial roasters, such as continuous belt roasters or rotary drum roasters, are employed to ensure even roasting. The peanuts are exposed to temperatures ranging from 320 degrees Fahrenheit to 350 degrees Fahrenheit for a specific duration, typically between 30 to 60 minutes. The exact time and temperature are carefully controlled and adjusted based on factors like peanut variety and moisture content to achieve the optimal roast profile. During roasting, the Maillard reaction, a chemical interaction between amino acids and reducing sugars, occurs, contributing to the development of complex flavor compounds and the characteristic golden brown color of the peanuts. Continuous monitoring of temperature and airflow within the roasters ensures uniform roasting and prevents over or undercooking, which could compromise the flavor and quality of the peanut butter filling. Once roasting is complete, the peanuts are rapidly cooled to halt the cooking process and preserve their flavor profile. This is typically achieved by passing the hot peanuts through cooling conveyors equipped with powerful fans that circulate ambient air. Rapid cooling prevents the peanuts from continuing to cook from residual heat, which could lead to undesirable flavor changes or textural issues. After cooling, the peanuts are transferred to blanching machines, where their skins are removed. Blanching involves exposing the peanuts to steam or hot air to loosen the skins, followed by mechanical rubbing or abrasion to peel them away. This step is essential, as peanut skins can impart a bitter taste and affect the smoothness of the peanut butter. The blanched peanuts are then inspected once more to ensure all skins and any remaining impurities have been effectively removed. The blanched peanuts are now ready for grinding, a critical step in transforming them into the creamy peanut butter that fills each Reese's cup. The peanuts are fed into industrial grinders, which consist of a series of grinding plates or mills that progressively reduce the peanut particles to the desired consistency. The initial grinding stage breaks the peanuts into coarse pieces, while subsequent stages further refine the texture, resulting in a smooth, creamy peanut butter. Throughout the grinding process, the peanuts' natural oils are released, contributing to the creamy consistency of the peanut butter. To achieve the perfect texture and prevent oil separation, stabilizers such as hydrogenated vegetable oils may be added. These stabilizers help maintain the emulsion of peanut solids and oils, ensuring the peanut butter remains smooth and spreadable over time. Temperature control during grinding is paramount. Excessive heat generated by friction can alter the flavor and consistency of the peanut butter. To mitigate this, cooling systems are integrated into the grinding equipment, maintaining the peanut butter at an optimal temperature and preserving its quality. Once the peanut butter reaches the desired consistency, it is transferred to stainless steel storage tanks equipped with agitation systems. These systems keep the peanut butter uniformly mixed, preventing the settling of solids and ensuring consistency across batches. The storage tanks are part of a closed system that protects the peanut butter from exposure to air and potential contaminants, preserving its freshness and flavor until it is needed for the next stage of production. Now, it's time to delve into the preparation of the chocolate coating that envelops the peanut butter filling, giving Reese's peanut butter cups their iconic taste and texture. The chocolate used is a carefully formulated blend designed to complement the peanut butter's flavor while providing a smooth and satisfying mouthfeel. The process begins with the selection of premium cocoa beans, sourced from regions known for their high-quality cocoa production, such as West Africa and South America. These beans are fermented and dried at their origin to develop the foundational flavor characteristics essential for quality chocolate. Upon arrival at the manufacturing facility, the cocoa beans undergo roasting, a process that further develops their flavor and reduces moisture content. Industrial-scale roasters, similar to those used for peanuts, are employed to ensure even roasting. The beans are roasted at temperatures between 250 degrees Fahrenheit to 320 degrees Fahrenheit for durations ranging from 30 to 60 minutes, depending on the desired flavor profile. Continuous monitoring ensures consistency and prevents over-roasting, which could impart bitter notes to the chocolate. After roasting, the cocoa beans are cooled and subjected to winnowing, a process that removes the outer shells, leaving behind the valuable cocoa nibs. These nibs are then ground into cocoa mass, also known as cocoa liquor, which serves as the base for all chocolate products. The grinding process generates heat, causing the cocoa butter within the nibs to melt and form a liquid mass. To create milk chocolate, the variety used in Reese's peanut butter cups, the cocoa mass is combined with specific proportions of sugar, milk solids, and additional cocoa butter. This mixture undergoes refining, where it is passed through a series of rollers to reduce particle size, resulting in a smoother texture. Achieving the optimal particle size is crucial, as it influences the mouthfeel and overall quality of the chocolate. Following refining, the chocolate mixture undergoes conching, a process involving continuous mixing and aeration at controlled temperatures. Conching serves multiple purposes. It further smooths the texture, develops flavor by promoting the evaporation of undesirable volatile compounds, and ensures a homogeneous blend of ingredients. The duration and temperature of conching are carefully controlled, with longer conching times typically resulting in superior flavor development. Once conching is complete, the chocolate is tempered to stabilize its crystalline structure. Tempering involves carefully cooling and reheating the chocolate to specific temperatures, encouraging the formation of stable cocoa butter crystals. Proper tempering ensures that the chocolate sets with a glossy finish, has a satisfying snap, and resists blooming, a condition where fat or sugar crystals rise to the surface, creating a dull or streaked appearance. The tempered chocolate is maintained at a precise temperature in holding tanks, ready for the enrobing process. These tanks are equipped with gentle agitation systems to keep the chocolate uniformly mixed and at the correct viscosity for coating the peanut butter filling. But up next is the integration of the peanut butter filling and the chocolate coating, a process that demands precision and synchronization to achieve the perfect balance between the two components. Specialized machinery is employed to deposit measured amounts of peanut butter onto a base layer of chocolate, ensuring consistency in size and weight for each cup. The process begins with the formation of the chocolate shell. Molds, typically made of polycarbonate or stainless steel, are filled with a specific amount of tempered milk chocolate, dispensed through precision-controlled nozzles. These molds then pass through a vibration station which ensures the chocolate evenly coats the bottom and sides of the mold cavity. This vibration also helps eliminate any air bubbles that could compromise the integrity or appearance of the finished product. The amount of chocolate deposited and the intensity of vibration are both tightly regulated, ensuring uniformity across thousands of cups produced per hour. Once the molds are coated, they are inverted and lightly spun in a controlled environment. This inversion allows excess chocolate to drain off while still leaving a consistent layer adhered to the inner surfaces of each mold. This stage is crucial. Too much chocolate can overwhelm the peanut butter filling, and too little can lead to structural failure of the cup during demolding or packaging. The molds then proceed through a cooling tunnel, typically kept at temperatures between 45 degrees Fahrenheit and 55 degrees Fahrenheit. The cooling phase ensures that the chocolate shell partially sets to the correct hardness before it receives the peanut butter filling. As the molded chocolate shells emerge from the cooling tunnel, they are transported to the filling station. Here, a high-speed depositor arm, equipped with precision temperature and viscosity control, deposits the peanut butter filling into each partially set chocolate cup. The filling temperature is typically maintained between 85 degrees Fahrenheit and 95 degrees Fahrenheit, warm enough to flow smoothly, but cool enough not to melt or deform the chocolate shell. The depositor is calibrated to deliver an exact volume of filling per cup, down to a fraction of a milliliter. This exactness is essential for product consistency and for ensuring that the peanut butter doesn't spill over the edges when the top chocolate layer is added. The formulation of the peanut butter filling used in Reese's is slightly different from traditional peanut butter. It is intentionally thicker and drier in consistency, achieved by controlling the moisture content and fat levels during the grinding and mixing process. This formulation helps the filling maintain its shape during deposition. and ensures it doesn't mix into or bleed through the surrounding chocolate. The peanut butter also contains a precise blend of sugar, salt, and stabilizers, all tailored to produce the sweet, slightly salty, and crumbly texture unique to Reese's cups. After the filling is deposited, the molds move on to receive the final chocolate layer. This top layer of tempered chocolate is again dispensed with precision, covering the peanut butter entirely and sealing the cup. The exact thickness of this layer is calibrated to ensure a perfect balance between the two flavors, and to provide structural integrity once the product is unmolded. If the chocolate top is too thin, it risks cracking during cooling and handling. Too thick, and it throws off the flavor harmony. The fully assembled peanut butter cups then enter a second cooling tunnel. This tunnel is longer and colder than the first, typically operating between 35 degrees Fahrenheit and 45 degrees Fahrenheit. Here, the final chocolate layer sets completely, bonding with the underlying components and solidifying the cup into its final form. Conveyor belts inside the tunnel are carefully speed regulated so that the cups spend the exact amount of time needed to fully crystallize the cocoa butter without overcooling, which could lead to bloom or textural issues. As the cooled and fully set cups exit the tunnel, they are transported to the demolding station. This is a delicate and crucial phase where the now solid chocolate cups must be removed from their molds without cracking, chipping, or leaving any residue behind. Modern factories use pneumatic or mechanical release systems that gently flex the molds while applying a quick burst of air from underneath each cavity. This loosens the cups and lifts them onto a secondary conveyor without physical contact from human hands, preserving hygiene and preventing product damage. Now it's time to go into the inspection and quality control stage, a multi-layered process where each Reese's peanut butter cup is evaluated for conformity, appearance, and safety. As the demolded cups travel along the inspection conveyor, they pass through high-resolution vision systems equipped with artificial intelligence software that scans for imperfections. This includes checking for chips in the chocolate, uneven layers, off-center fillings, or improperly formed edges. Cups that do not meet the strict visual criteria are automatically rejected by air jets that direct them off the main line and into collection bins for disposal or reprocessing, depending on company policy and food safety regulations. In addition to visual checks, random samples are pulled at regular intervals for more in-depth testing. These samples are weighed to ensure they meet exacting product specifications. Other tests may include breaking the cup in half to examine the internal peanut butter to chocolate ratio, or using texture analyzers that measure the product's resistance to pressure, an indicator of proper tempering and filling density. Chemical testing is also conducted regularly to verify the correct balance of sugar, moisture, fat, and salt in the filling. These tests are often performed in on-site quality control laboratories, where technicians run batch samples through a range of analytical equipment, such as moisture analyzers, gas chromatographs, and spectrophotometers. If any irregularities are found, production is paused, and corrective measures are implemented. This could mean recalibrating a depositor nozzle, adjusting roasting temperatures for peanuts, or even reviewing the supply chain for ingredient inconsistencies. But up next is the packaging stage, which begins with the alignment of the peanut butter cups into lanes that feed into high-speed wrapping machines. These machines are capable of wrapping hundreds of cups per minute, and they must do so without damaging the fragile chocolate shell. The wrapper material is typically a laminated foil paper composite, selected for its barrier properties against oxygen, moisture, and light, all of which can degrade product quality over time. Each wrapper is printed with the Reese's branding, product information, batch codes, and expiration dates using thermal or inkjet printers. As the cups enter the wrapping station, they are placed onto rotating belts that synchronize with the wrapper feed. A roll of pre-printed wrapping film is continuously pulled into position, cut to size by high-speed blades, and sealed around each cup using heated crimpers. The sealing temperature and pressure must be carefully controlled to ensure an airtight seal without melting the chocolate inside. Once wrapped, the cups are grouped for secondary packaging. They may be placed in cardboard sleeves, plastic trays, or directly into multi-unit bags, depending on the product configuration. These groups are then placed into larger cartons for shipping. Before sealing, a final barcode scanner checks each item to confirm it matches the correct SKU and batch. Any errors trigger an automatic halt in the packing line to prevent cross-contamination between different product types. Every carton is weighed and scanned one final time before being sealed, labeled, and moved to the warehouse staging area. From here, pallets of Reese's peanut butter cups are logged into an inventory system and scheduled for distribution to retail locations across the country. Every step from peanut to pallet is tracked with traceability data, ensuring full accountability throughout the production cycle. Now it's time to go into the warehousing and distribution phase of Reese's peanut butter cup production, where the finished products transition from tightly controlled factory environments to large-scale logistics operations. Once the individually wrapped and secondary packaged cups are assembled into master cartons, these cartons are loaded onto pallets. Each pallet holds a predefined number of cartons, strategically arranged to optimize space while maintaining product integrity during transport. Automated palletizers equipped with robotic arms or gantry systems handle this process with precision, stacking cartons with minimal human intervention to ensure efficiency and reduce labor costs. Once a pallet is completed, it's secured using high-tensile stretch wrap, often applied via automated rotary arm or turntable wrapping machines. This stretch film not only stabilizes the load, but also provides a moisture and dust barrier, safeguarding the products during storage and shipping. Pallets are then labeled with barcoded shipping tags that include vital information such as product codes, batch numbers, production dates, and destination data. These barcodes are integrated into the factory's centralized inventory management system, allowing for real-time tracking and traceability from the moment a product leaves the production floor. The wrapped and labeled pallets are then moved to climate-controlled storage areas within the facility's warehouse. These storage zones are maintained at stable temperatures, typically between 55 degrees Fahrenheit and 70 degrees Fahrenheit, to ensure the chocolate remains in perfect condition. Extreme heat can cause melting or blooming, while excessive cold may alter texture or create condensation that can compromise the packaging seal. Environmental sensors continuously monitor these storage areas, and any deviation outside preset tolerances triggers alerts for immediate corrective action. Warehouse operations are managed by advanced warehouse management systems, which direct the flow of goods through automated guided vehicles or forklifts, guiding them to the optimal racking locations based on FIFO principles. This ensures older inventory is shipped before newer batches, reducing the risk of aging stock reaching consumers. Some high-output facilities even use fully automated storage and retrieval systems, where robotic cranes handle all inbound and outbound movement of pallets without human inputs. As orders come in from distribution centers, retail chains, or e-commerce platforms, the WMS generates pick lists, directing operators or picking robots to assemble the correct products for shipment. During the picking process, each item's barcode is scanned again to confirm accuracy. Pallets are then loaded onto temperature-controlled trucks or shipping containers, with the logistics team carefully planning routes and loading sequences to match delivery schedules. The transportation phase is critical in preserving product quality. Trucks used to transport Reese's peanut butter cups are often equipped with refrigeration units to maintain stable conditions, especially during warmer months or in hot climates. Real-time GPS tracking and telematics systems allow logistics managers to monitor vehicle locations and environmental conditions inside the trailers, ensuring any issues can be addressed proactively. Once the Reese's cups arrive at regional distribution centers, they're cross-docked or stored temporarily before being sent to individual retail locations. Cross-docking minimizes storage time by immediately transferring incoming goods to outgoing trucks, improving freshness and reducing inventory holding costs. At the retail level, automated shelf replenishment systems and electronic point-of-sale data further refine logistics by signaling when to restock based on actual consumer purchases, closing the loop between factory and final sale. Now it's time to explore the role of factory automation and digital systems that underpin every phase of Reese's peanut butter cup production. From peanut sorting to final product distribution, automation enhances consistency, efficiency, and food safety across the board. At the front end of the process, smart sensors and machine vision systems oversee raw ingredient inspection. These tools can detect flaws invisible to the human eye, such as slight discoloration, mold, or the presence of foreign matter, ensuring that only the highest quality peanuts and cocoa beans enter the process. Programmable logic controllers orchestrate the flow of operations on the production line. These industrial computers are connected to every piece of equipment, from roasters and grinders to depositors and cooling tunnels, and execute real-time instructions based on input data. For example, if a change in peanut moisture content is detected by inline sensors, the PLC can automatically adjust roasting time or temperature to compensate, maintaining flavor consistency. Supervisory control and data acquisition systems provide plant operators with a bird's-eye view of the entire production environment. With these interfaces, managers can monitor batch progress, verify line speeds, track downtime, and receive alerts if any machinery falls out of spec. Every action taken by machines is logged for traceability, which is particularly important for food safety compliance and auditing purposes. Data collected from SCADA systems can also be analyzed for continuous improvement, helping to identify bottlenecks, optimize throughput, and reduce energy consumption. Robotics play a crucial role in packaging and material handling. Articulated robotic arms, equipped with suction grippers or vision-guided end effectors, perform tasks such as picking and placing cups into trays, applying labels, or stacking cartons. These robots can work around the clock without fatigue, dramatically improving productivity while maintaining precision and reducing injury risk for human workers. Factory hygiene and sanitation are also managed with the help of automation. Clean-in-place systems are installed throughout the facility to automatically flush and sanitize processing lines between batches. These systems circulate heated cleaning solutions through tanks, pipes, and machinery to remove peanut residue and chocolate buildup, all without disassembling equipment. Sensors measure cleaning effectiveness in real time, ensuring that microbial standards are met and that no allergenic cross-contact occurs between production cycles. But up next is the innovation behind product design and the proprietary formulation that gives Reese's peanut butter cups their legendary status. While the general public recognizes the product for its flavor, texture, and iconic shape, much of the success lies in the precise engineering of ingredients and design. The ratio of peanut butter to chocolate has been refined over decades of experimentation, resulting in a balance that optimizes sweetness, saltiness, creaminess, and firmness. Hershey's R&D teams use texture analysis, sensory panels, and predictive modeling to test thousands of variations in ingredient proportions before locking in a final formula. Ingredient consistency is paramount. For instance, the type of sugar used in the peanut butter filling is selected not just for sweetness, but for its ability to control water activity and crystallization during storage. The salt content is finely tuned to enhance the peanut flavor without becoming overpowering, while milk powder used in the chocolate is selected for both its taste and its emulsifying properties. Even minor fluctuations in these ingredients can affect the final mouthfeel and flavor, which is why tight supplier controls and internal batch testing are enforced. The cup shape and wrapper design are also engineered with precision. The signature fluted edge of each Reese's cup isn't just a visual cue, it aids in demolding and adds structural strength. The cups are formed using molds with concentric grooves that create this pattern as chocolate is spun or vibrated up the walls. The wrapper is designed to peel off easily without sticking to the chocolate, which requires selecting specific coatings and materials that interact correctly with cocoa butter at varying humidity levels. In recent years, innovation has also extended to creating new product lines, miniatures, thins, big cups, and seasonal shapes. Each variant requires its own custom set of tooling, depositor calibrations, and process flow adjustments to accommodate differences in fill volume, chocolate thickness, and packaging format. These product changes often involve months of pilot testing on R&D lines before being scaled to full production. Engineers simulate the behavior of chocolate and peanut butter under different conditions using computational fluid dynamics models, ensuring that no matter the shape or size, the Reese's experience remains consistent. Every year, the production line adapts to create special seasonal versions of Reese's peanut butter cups, which introduces another layer of complexity to the manufacturing process. For Halloween, pumpkin-shaped cups are crafted, while Christmas brings tree-shaped varieties and Easter features egg-shaped versions, all of which require entirely different molding systems. Instead of the standard fluted cup molds used year-round, these limited editions use custom-engineered molds with unique contours that must still ensure even chocolate distribution, stable cooling, and a clean release during demolding. These seasonal shapes often necessitate recalibrating the chocolate depositor systems and modifying the cooling tunnel timings, since broader or thicker designs may set at different rates than standard cups. The process begins with the careful selection and sourcing of raw ingredients. The primary components of KitKat bars include wheat flour, sugar, cocoa mass, cocoa butter, milk powder, vegetable oils, and emulsifiers. Nestlé, the brand behind KitKat, sources these ingredients from various regions worldwide, ensuring sustainability and adherence to strict quality standards. The cocoa used in KitKat is primarily sourced from the Nestlé Cocoa Plan, which promotes sustainable farming practices and fair trade. Once the raw materials arrive at the production facility, they undergo a series of inspections and tests to verify purity, consistency, and compliance with food safety regulations. This includes spectroscopic analysis for contaminants, moisture content testing, and sensory evaluations conducted by trained professionals. Once approved, the ingredients are stored in temperature-controlled silos and dispensing systems. The flour is kept in airtight storage to prevent contamination, while cocoa and milk powder are maintained under controlled humidity conditions to prevent clumping. Automated feeding systems transport these raw materials to the respective processing units, ensuring precise measurement and consistency in formulation. The first major step in KitKat production is wafer baking. The signature light and crispy wafer layers are created through a precise blending of wheat flour, water, sugar, and vegetable oils. Large industrial mixers, equipped with programmable logic controllers, ensure thorough mixing to produce a smooth and homogeneous batter. Once mixed, the batter is transferred via pressurized pumps to high-speed continuous wafer baking ovens. These ovens feature rotating baking plates that evenly distribute the batter across the surface, forming thin sheets of wafer. The baking plates operate at carefully controlled temperatures, typically around 180 to 200 degrees Celsius, ensuring uniform texture and color. The baked wafer sheets emerge golden brown and crisp, ready for the next stage. To enhance the crispness, the wafer sheets pass through a controlled cooling system. Conveyor belts transport the freshly baked wafers through a cooling tunnel, where calibrated fans gradually reduce the temperature to prevent thermal shock. The cooled wafers are then directed to the trimming and cutting station. Automated guillotine cutters trim the edges of the wafers to achieve uniform dimensions, ensuring consistency across all KitKat bars. Once trimmed, the wafers are transported to the layering station. Here, a fine layer of chocolate cream filling made from a precise blend of cocoa, sugar, and milk powder is evenly spread onto the wafers. Automated depositor machines ensure the filling is applied uniformly, maintaining the right thickness for optimal texture. The layering process continues with additional wafer sheets stacked on top, creating a multi-layered wafer slab. These slabs are then pressed under controlled pressure to bond the layers together without crushing the delicate structure. After layering, the wafer slabs proceed to the cutting stage. High-speed rotary or ultrasonic blade systems slice the large wafer sheets into precise rectangular portions, forming the individual KitKat fingers. Ultrasonic cutting technology is particularly effective in ensuring clean, precise cuts without generating excess crumbs or damaging the layers. The next crucial step is chocolate enrobing. The enrobing process begins with the preparation of molten milk chocolate, which is produced in large conching machines. These machines continuously grind and blend cocoa mass, cocoa butter, sugar, and milk powder, refining the mixture to achieve a smooth, velvety consistency. The conching process, which can last several hours, helps develop the rich, creamy texture and enhances the flavor profile of the chocolate. Once ready, the molten chocolate is fed into enrobing machines, where KitKat fingers pass through a curtain-like flow of chocolate. These enrobers ensure complete coverage, with excess chocolate removed using controlled air jets and vibrating conveyors. To achieve the signature glossy finish, the enrobed bars pass through a tempering unit, which carefully regulates the chocolate's crystallization process. This involves a precise cycle of heating, cooling, and reheating to stabilize the cocoa butter crystals, preventing bloom and ensuring a smooth, even texture. Following enrobing, the chocolate-covered KitKat bars enter a cooling tunnel. This tunnel, equipped with multi-zoned cooling technology, gradually reduces the temperature in stages to solidify the chocolate coating without causing cracks or condensation. The cooling process is carefully monitored using infrared sensors to maintain consistency. Once the chocolate is fully set, the KitKat bars move to the quality control and inspection stations. Advanced vision inspection systems, equipped with high-resolution cameras, scan each bar for defects, such as uneven coating, improper sizing, or misaligned layers. Bars that do not meet quality standards are automatically rejected by robotic sorting arms and sent for reprocessing. Additional quality checks include weight verification, moisture content analysis, and sensory testing conducted by trained specialists. After passing inspection, the KitKat bars are transported to high-speed wrapping machines. Individual bars are wrapped in foil or plastic film using heat sealing technology, ensuring airtight packaging that preserves freshness. These wrapped bars are then grouped into multi-packs, which are subsequently boxed using robotic case packers. The packaging design is carefully printed with product details, barcodes, and branding elements before final sealing. The packaged KitKat bars are then palletized for distribution. Automated palletizing systems stack the boxes onto pallets in a precise arrangement to optimize space utilization during transportation. These pallets are shrink-wrapped for stability and loaded onto temperature-controlled trucks for delivery to distribution centers worldwide. The logistics process is carefully coordinated to ensure timely delivery, with real-time tracking systems monitoring shipments from factory to retailer. Throughout the entire production process, extensive quality control measures are in place to uphold product integrity. Each batch undergoes rigorous laboratory testing, including microbiological screening, allergen testing, and texture analysis. Data from all processing stages is logged in automated tracking systems, allowing full traceability and compliance with food safety regulations. While the fundamental principles of KitKat production remain consistent across different manufacturing plants, regional variations may exist to cater to local tastes and preferences. For example, KitKat flavors such as matcha green tea, strawberry, and sake are produced in Japan using specialized formulations. Some factories may also incorporate alternative chocolate blends, varying cocoa content to suit market demands. Nestlé continues to innovate and optimize KitKat production through advancements in automation, sustainability initiatives, and ingredient sourcing. Modern factories are increasingly utilizing AI-driven quality control systems, energy-efficient processing equipment, and eco-friendly packaging solutions to reduce environmental impact. With continuous improvements in manufacturing technology, KitKat remains a global favorite, offering consumers a consistently delightful chocolate experience in every bite. Mars bars, one of the most iconic chocolate confections in the world, are produced in highly sophisticated manufacturing facilities designed to ensure consistency, efficiency, and quality at every step of the process. The production of Mars bars involves multiple intricate stages, from sourcing and processing raw ingredients to forming, enrobing, cooling, and packaging the final product. Each step is meticulously controlled using advanced automation technology and stringent quality control measures to ensure the signature caramel, nougat, and chocolate combination is perfectly replicated in every bar. The process begins with the careful selection of raw ingredients. The main components of a Mars bar include sugar, cocoa mass, cocoa butter, skimmed milk powder, whey powder, palm fat, glucose syrup, lactose, milk fat, and egg whites. These ingredients are sourced from trusted suppliers and undergo rigorous quality assurance checks upon arrival at the factory. Sugar, which plays a crucial role in both the nougat and caramel layers, is stored in large silos, where it is kept dry and free from contamination. Cocoa products, including cocoa mass and cocoa butter, are stored in climate-controlled environments to prevent degradation. Dairy ingredients, such as skimmed milk powder and whey powder, are tested for purity and consistency before use. Once the raw ingredients are approved, the first major stage in Mars bar production is the creation of the nougat layer. Nougat is a key structural component of the bar, providing a soft, chewy texture that contrasts with the caramel and chocolate. The nougat making process begins in large industrial mixing tanks, where a combination of sugar, glucose syrup, and water is heated to create a syrup. This syrup is then aerated using a whipping system, which incorporates fine air bubbles to achieve the desired light and fluffy texture. During this stage, egg whites or hydrolyzed soy protein are added as stabilizers to maintain the nougat's consistency. Once the nougat mixture reaches the proper texture, it is transferred onto a continuous conveyor belt, where it is spread into an even layer. This belt passes through a cooling tunnel to allow the nougat to set before it reaches the next stage of the process. The cooled nougat layer is then precisely cut into rectangular strips using high-speed guillotine cutters. These strips will form the base of each Mars bar. The next step in the process is the caramel layer. The caramel used in Mars bars is created through a controlled cooking process that involves heating sugar, glucose syrup, and milk ingredients to high temperatures. This process requires careful monitoring to achieve the perfect balance of sweetness and viscosity. Industrial batch cookers equipped with automated temperature controls ensure that the caramel reaches the ideal consistency before it is deposited onto the nougat base. The caramel is applied as a continuous sheet over the nougat layer, ensuring even distribution and uniform thickness. Once the caramel is applied, the combined nougat and caramel layers proceed through a controlled cooling tunnel, where the temperature is gradually reduced to allow the caramel to set without becoming too hard or sticky. This ensures that the layers remain cohesive and easy to cut in the next stage of production. After cooling, the layered nougat and caramel sheets are fed into an automated cutting system, which uses precision blades to slice them into individual bar-sized portions. These freshly cut bars are then transported via conveyor belts to the enrobing station, where they receive their final chocolate coating. The enrobing process is a critical step in Mars bar production, as it gives the bars their signature smooth milk chocolate exterior. The chocolate coating is made from a blend of cocoa mass, cocoa butter, sugar, and milk powder, which is carefully tempered to achieve the perfect texture and glossy finish. The tempering process involves heating and cooling the chocolate in a controlled manner to ensure the cocoa butter crystals form a stable structure, preventing fat bloom and ensuring a smooth mouthfeel. At the enrobing station, the cut nougat and caramel bars pass through a curtain-like waterfall of molten chocolate, which fully coats them. Excess chocolate is removed using controlled air jets and vibrating conveyors to ensure an even layer without excessive buildup. Some factories use a two-stage enrobing process, where an initial thin layer of chocolate is applied as a base coat before the final, thicker chocolate layer is added. After enrobing, the chocolate-covered bars enter a multi-zone cooling tunnel, which gradually reduces their temperature in controlled stages. This cooling process allows the chocolate to set properly without developing cracks or a dull surface. The bars emerge from the cooling tunnel with a perfectly set chocolate shell, ready for the final stages of quality control and packaging. Quality control is a fundamental part of Mars bar production, ensuring that only bars meeting strict standards reach consumers. Automated vision inspection systems equipped with high-resolution cameras scan each bar for defects such as uneven coating, misshapen forms, or inconsistencies in size. Bars that do not meet the required specifications are automatically rejected and sent for reprocessing. Additional quality control measures include weight checks using precision weighing systems, texture analysis, and sensory evaluations conducted by trained specialists. Once the bars pass quality inspection, they proceed to the packaging area, where high-speed wrapping machines individually wrap each bar in foil or plastic film. These machines use heat sealing technology to create airtight packaging that preserves freshness and prevents contamination. The wrapped bars are then grouped into multi-packs and placed into branded cartons, which are sealed and labeled using automated case packing systems. The final step in the process is palletization and distribution. Automated palletizing systems stack the packaged bars onto pallets in a precise arrangement to optimize space utilization during transportation. The pallets are shrink-wrapped for stability and loaded onto temperature-controlled trucks for distribution to retail stores and supermarkets worldwide. The entire logistics process is carefully coordinated to ensure timely delivery while maintaining the product's freshness and quality. Throughout the entire manufacturing process, Mars maintains stringent quality control and food safety standards. Each production batch undergoes extensive laboratory testing, including microbial analysis, allergen testing, and moisture content verification. The company also invests in sustainable sourcing initiatives, ensuring that key ingredients such as cocoa and palm oil are responsibly sourced to minimize environmental impact. Different Mars manufacturing facilities may incorporate slight variations in processing techniques based on regional ingredient availability, consumer preferences, or proprietary formulations. Some facilities may use alternative chocolate blends with varying cocoa content to cater to specific markets, while others may modify the nougat formulation for textural differences. Additionally, Mars continuously invests in research and development to improve efficiency, reduce energy consumption, and enhance sustainability in its production processes. With advancements in automation, AI-driven quality control systems, and eco-friendly packaging innovations, the production of Mars bars continues to evolve while maintaining the signature taste and texture that consumers have loved for generations. Twix, one of the world's most beloved chocolate bars, is manufactured using a highly sophisticated and automated process that ensures each bar maintains its signature combination of crunchy biscuit, smooth caramel, and creamy milk chocolate coating. The production of Twix bars occurs in state-of-the-art factories that utilize precision engineering, cutting-edge food processing technology, and rigorous quality control protocols. From the sourcing of raw ingredients to packaging and distribution, every step is carefully orchestrated to guarantee consistency, efficiency, and superior taste. The process begins with the selection and procurement of high-quality raw materials. The key ingredients in Twix bars include wheat flour, sugar, palm oil, cocoa butter, skimmed milk powder, cocoa mass, lactose, whey powder, salt, and emulsifiers. These ingredients are sourced from carefully vetted suppliers who must meet strict food safety and sustainability requirements. For instance, the cocoa used in Twix bars is sourced through Mars' Cocoa for Generations initiative, ensuring ethical sourcing and environmental responsibility. Similarly, the palm oil used in the biscuits and caramel is certified sustainable to reduce environmental impact. Upon arrival at the manufacturing facility, the raw ingredients undergo thorough quality checks before entering the production process. These checks include spectroscopic analysis to detect contaminants, moisture content analysis to ensure freshness, and sensory evaluations to verify taste and aroma. Ingredients that meet the necessary standards are then stored in temperature-controlled silos and storage units to maintain their quality. The first step in the actual production process is the creation of the biscuit base. Twix bars are distinguished by their crunchy, shortbread-like biscuit layer, which requires precise preparation and baking. The process begins in large industrial mixers, where wheat flour, sugar, palm oil, and leavening agents are combined to form a dough. The mixing process is carefully timed to ensure the dough reaches the ideal consistency, firm enough to hold its shape during baking, yet tender enough to create the signature crisp texture. Once the dough is fully mixed, it is transferred to an automated sheeting system. This system rolls the dough into a uniform sheet of the exact thickness required for Twix bars. The sheeted dough then moves to a rotary cutting machine, which stamps out individual biscuit fingers. Each biscuit is precisely cut to ensure uniform size and shape, allowing for seamless assembly in later stages. The cut dough pieces are placed onto conveyor belts and transported into a large industrial baking oven. These ovens operate using a continuous baking system, where the biscuit fingers travel through different heat zones that gradually bake them to perfection. The baking temperature is carefully controlled, typically ranging between 180 to 200 degrees Celsius, 356 to 392 degrees Fahrenheit, ensuring that each biscuit is evenly baked to a golden brown. Advanced infrared sensors monitor the biscuits throughout the baking process, ensuring uniformity in color, texture, and moisture content. Once fully baked, the biscuits pass through a cooling tunnel that gradually reduces their temperature, preventing cracking or breakage. Next, the caramel layer is prepared. The caramel used in Twix bars is made from a precise blend of sugar, glucose syrup, milk, and butter. This mixture is heated in large stainless steel batch cookers, where it undergoes controlled caramelization. The temperature and cooking time are crucial in achieving the perfect consistency, thick enough to stay in place on the biscuit, but soft enough to deliver a smooth, chewy texture. Once the caramel reaches the desired consistency, it is transferred to a continuous depositor system. This machine evenly dispenses a uniform layer of caramel onto each biscuit. The caramel application must be carefully controlled to ensure consistency in thickness across all bars. Any inconsistencies could lead to difficulties in chocolate enrobing or affect the final texture. With the caramel applied, the bars move along the conveyor belt to a cooling station, where they pass through a controlled cooling tunnel. This tunnel gradually reduces the temperature of the caramel, allowing it to set properly while maintaining its soft, chewy texture. After cooling, the caramel-coated biscuits are ready for the enrobing process, where they will be covered in rich milk chocolate. The enrobing process is one of the most critical steps in Twix production. The milk chocolate coating is prepared in large conching machines, which continuously grind and refine cocoa mass, cocoa butter, sugar, and milk powder. This process enhances the texture and flavor of the chocolate, ensuring a smooth, creamy consistency. The chocolate is then tempered, a controlled heating and cooling process that stabilizes the cocoa butter crystals. Proper tempering is essential to achieving the signature glossy finish and preventing fat bloom, white streaks that can appear on improperly tempered chocolate. At the enrobing station, the caramel-topped biscuits pass through a continuous chocolate waterfall. This ensures that each bar is fully coated in an even layer of chocolate. Any excess chocolate is removed using controlled air jets and vibrating conveyors, which help distribute the chocolate evenly without excessive buildup. Some factories employ a two-stage enrobing process, where a thin base coat of chocolate is applied first to ensure better adhesion before the final, thicker chocolate layer is added. Once the bars are coated, they enter a multi-zone cooling tunnel. This tunnel is divided into different temperature zones that gradually reduce the temperature, allowing the chocolate to set perfectly without cracking or becoming dull. The bars emerge from the cooling tunnel with a firm, glossy chocolate coating, ready for the next stage of production. Quality control is a top priority at every stage of Twix production. After cooling, the bars pass through a series of automated inspection systems. High-speed vision cameras scan each bar for inconsistencies in chocolate coating, caramel distribution, and overall shape. Any bars that do not meet specifications are automatically rejected and sent for reprocessing. In addition to visual inspections, quality control teams conduct random weight checks, moisture analysis, and sensory evaluations to ensure that each batch meets Mars's stringent quality standards. Once the bars have passed inspection, they move to the packaging stage. Twix bars are individually wrapped using high-speed horizontal flow wrapping machines. These machines use heat-sealing technology to create airtight packaging that preserves freshness and prevents contamination. The wrapped bars are then grouped into multi-packs, which are sealed in branded cartons using automated case packing systems. After packaging, the final step in the process is palletization and distribution. Robotic palletizing systems stack the packaged bars onto pallets in precise arrangements, optimizing space for transport. The pallets are then shrink-wrapped for stability and loaded onto temperature-controlled trucks for distribution to retailers worldwide. Mars utilizes an advanced logistics network to ensure efficient delivery while maintaining product freshness. Throughout the entire production process, Mars adheres to strict food safety and sustainability standards. Each batch undergoes rigorous laboratory testing, including microbiological analysis, allergen testing, and texture verification. The company also invests in eco-friendly initiatives, such as reducing energy consumption in manufacturing and using recyclable packaging materials. Different Mars factories may employ slight variations in processing techniques based on regional ingredient availability and consumer preferences. For example, some regions may use alternative chocolate formulations with varying cocoa content, while others may adjust the caramel consistency based on market preferences. Additionally, limited edition Twix flavors, such as Twix white chocolate and Twix peanut butter, require modifications in ingredient formulation and processing techniques. As consumer demand for innovative flavors and healthier options grows, Mars continues to invest in research and development to improve Twix production. Recent advancements in AI-driven quality control, robotic automation, and sustainable ingredient sourcing are shaping the future of Twix manufacturing. Despite these innovations, the core principles of precision, consistency, and quality remain unchanged, ensuring that every Twix bar delivers the signature, crunchy, chewy, and chocolatey experience that consumers love. The making of a Hershey's chocolate bar is a complex, highly automated process that combines tradition with cutting-edge technology. From sourcing high-quality cocoa beans to wrapping the final product, every step is optimized for efficiency, consistency, and taste. The journey of a Hershey's bar begins with the careful selection of raw ingredients sourced from around the world. Cocoa, sugar, milk, and other ingredients are carefully tested to ensure they meet the company's high standards before they are transformed into the iconic chocolate bars that have been loved for generations. At the heart of every Hershey's chocolate bar is cocoa. The company sources its cocoa beans primarily from Ghana, Côte d'Ivoire, and Ecuador, regions known for producing high-quality beans with robust flavor profiles. Cocoa farmers in these areas harvest the ripe pods, extract the cocoa beans, and allow them to ferment for several days to develop their characteristic chocolatey taste. Once dried, the beans are shipped to Hershey's production facilities, where they undergo rigorous quality checks. Each shipment is tested for moisture content, flavor consistency, and the absence of contaminants. Only the highest quality beans make it through this stringent selection process. Once approved, the cocoa beans are sent to the roasting stage. Large industrial roasters expose the beans to carefully controlled heat, typically between 120 to 150 degrees Celsius, 248 to 302 degrees Fahrenheit, depending on the desired flavor profile. The roasting process is essential for developing the deep, complex flavors of chocolate. Different roasting profiles are used depending on whether the beans will be used for milk chocolate, dark chocolate, or other specialty products. After roasting, the cocoa beans enter the winnowing process. Specialized machinery cracks the roasted beans and removes the outer husks, leaving behind the valuable cocoa nibs. These nibs contain both the cocoa solids and cocoa butter needed for chocolate production. The nibs are then ground into a thick, dark paste known as chocolate liquor, which contains no alcohol despite its name. This chocolate liquor is the base for all Hershey's chocolate products. For Hershey's classic milk chocolate bars, chocolate liquor is combined with sugar, milk, and cocoa butter. The milk used in Hershey's chocolate is a key ingredient that gives it its distinctive taste. Unlike many European chocolates that use powdered or condensed milk, Hershey's uses fresh milk sourced from dairy farms in Pennsylvania and surrounding states. The milk is pasteurized and condensed before being blended with sugar to create a sweet, creamy base. The next stage in the process is refining. The chocolate mixture is run through a series of steel rollers that grind the particles to an ultra-fine consistency. This refining process is crucial for creating a smooth, melt-in-your-mouth texture. The finer the particles, the smoother the final chocolate will be. Once refined, the chocolate undergoes conching, a critical process that enhances flavor and texture. Conching machines, which resemble large industrial mixers, continuously stir the chocolate at controlled temperatures for several hours. This process aerates the chocolate, allowing unwanted acidic compounds to evaporate while enhancing its creamy mouthfeel. Hershey's uses a proprietary conching method that contributes to its signature flavor, which has a slightly tangy undertone due to controlled acidity in the milk. After conching, the chocolate moves to the tempering stage. Tempering is the process of heating and cooling chocolate in a precise manner to stabilize the cocoa butter crystals. Proper tempering ensures that Hershey's bars have a glossy finish, a firm snap, and a long shelf life. If the chocolate were not tempered correctly, it could develop fat bloom, a whitish streaking effect caused by unstable cocoa butter. Now, the tempered chocolate is ready for molding. Automated machines pour precise amounts of liquid chocolate into bar-shaped molds, which are then vibrated to remove air bubbles and ensure even distribution. The molds travel along a conveyor system into a cooling tunnel, where the chocolate solidifies into its final shape. Once cooled, the bars are ejected from their molds and transported via conveyor belts to the packaging area. Here, high-speed wrapping machines encase each bar in foil and branded paper sleeves, protecting the chocolate from moisture and light while ensuring a fresh, appealing presentation. Throughout the entire process, strict quality control measures are in place. High-resolution vision inspection systems scan each bar for defects, such as air bubbles, improper molding, or size inconsistencies. Bars that do not meet specifications are automatically rejected and sent for reprocessing. Additionally, random sensory evaluations are conducted by trained taste testers to ensure that the flavor, texture, and overall quality remain consistent. Once packaged, the final step is palletization and distribution. Automated robotic arms stack the packaged bars onto pallets, which are then shrink-wrapped for stability. These pallets are loaded onto temperature-controlled trucks and shipped to retailers worldwide. Hershey's operates an advanced logistics network that ensures timely delivery while maintaining product freshness. The entire manufacturing process is designed for efficiency, consistency, and sustainability. Hershey's continues to invest in eco-friendly initiatives, such as reducing water and energy consumption in production, using ethically sourced cocoa, and optimizing packaging materials to minimize waste. Different Hershey's factories may employ slight variations in processing techniques based on regional preferences and ingredient availability. Additionally, specialty products like Hershey's cookies and cream bars or Hershey's dark chocolate require modifications in ingredient formulation and processing times. As the chocolate industry continues to evolve, Hershey's remains at the forefront of innovation, combining tradition with advanced manufacturing techniques to produce its iconic chocolate bars. Through precision engineering, strict quality control, and a commitment to excellence, Hershey's ensures that every bar delivers the same beloved taste that generations have enjoyed. The making of Toblerone, the iconic triangular chocolate bar, is a masterclass in precision engineering, premium ingredient selection, and automated manufacturing processes. Unlike conventional chocolate bars, Toblerone stands out for its distinctive shape, rich Swiss milk chocolate, and the inclusion of honey and almond nougat. Every step, from sourcing the finest ingredients to molding the signature peaks, is meticulously controlled to ensure quality, consistency, and adherence to the Swiss chocolate making tradition. The process begins with sourcing high-quality ingredients. Toblerone's signature flavor comes from its carefully selected components: Swiss milk, sugar, cocoa mass, cocoa butter, honey, almonds, and egg whites. The milk, sourced from Swiss dairy farms, is a critical ingredient that contributes to the creamy texture. The cocoa is sourced from sustainable farms in Ghana and Ecuador, where beans are hand-harvested, fermented, and dried under strict quality control measures. Almonds are procured from select suppliers, ensuring they meet the required standards of size, flavor, and crunch. The honey, a key component that adds a subtle sweetness, is sourced from European beekeepers specializing in high-quality aromatic varieties. Once the ingredients arrive at the production facility, they undergo rigorous quality checks. Advanced spectroscopic analysis, moisture content testing, and flavor profiling ensure that each ingredient meets the brand's high standards. The cocoa beans are then roasted at carefully controlled temperatures to develop their deep, complex flavor. Different roasting profiles are used depending on whether the beans will be used for Toblerone's milk, dark, or white chocolate variations. After roasting, the cocoa beans move to the winnowing stage, where high-powered machinery cracks them open and removes the husks. The remaining cocoa nibs, which contain the essence of the chocolate, are then finely ground into a thick, rich paste known as chocolate liquor. This forms the base of Toblerone's chocolate. The chocolate liquor is blended with sugar, cocoa butter, and Swiss milk powder to create the signature, smooth and creamy chocolate mixture. The next step in the process is refining. The chocolate mixture passes through a series of heavy-duty steel rollers that break down the particles to an ultra-fine consistency. This is crucial in achieving the signature melt-in-your-mouth texture. The refining process also helps blend the ingredients evenly, ensuring a perfectly smooth mixture. Following refining, the chocolate undergoes conching, a process that enhances its texture and flavor. Large conching machines continuously mix, aerate, and heat the chocolate for several hours, allowing volatile acids to evaporate and the flavors to develop fully. Toblerone's conching process is fine-tuned to create a silky texture and a well-rounded, rich taste. Meanwhile, the honey and almond nougat mixture is prepared in a separate area of the factory. Sugar, honey, and egg whites are heated and aerated to create a light, chewy nougat. Almonds, which have been roasted to bring out their nutty aroma, are chopped into small pieces and folded into the nougat mixture. The nougat is then cooled and ground into fine pieces before being incorporated into the chocolate. Once the chocolate has completed the conching process, the finely ground nougat mixture is carefully folded into it, ensuring even distribution. This step is crucial in maintaining the signature texture and taste of Toblerone. With the chocolate and nougat mixture fully blended, the next stage is tempering. Tempering is a precise process of heating and cooling chocolate in a controlled manner to stabilize the cocoa butter crystals. Proper tempering ensures that the chocolate has a glossy finish, a firm snap, and a smooth texture. Toblerone's tempering process is carefully calibrated to achieve the ideal consistency before molding. Molding is where Toblerone's iconic shape comes to life. The tempered chocolate is poured into custom-designed triangular molds that give the bar its distinctive peaks. The molds are gently vibrated to remove air bubbles and ensure even distribution of the chocolate. After molding, the bars pass through a cooling tunnel, where they are gradually cooled to allow the chocolate to set perfectly without cracks or imperfections. Once solidified, the bars are removed from the molds and transported to the quality control station. Each bar is inspected using high-resolution vision cameras, which detect any inconsistencies in shape, texture, or coating. Automated sorting systems remove any defective bars, ensuring that only perfectly shaped Toblerone bars proceed to packaging. The packaging process is designed to maintain the freshness and integrity of the chocolate. Toblerone bars are individually wrapped in foil to protect them from moisture and light, then placed into the iconic triangular cardboard cartons. High-speed packaging machines fold and seal the cartons with precision, ensuring that the bars remain securely enclosed. Following packaging, the bars are palletized using robotic systems, stacked carefully for stability during transport. These pallets are shrink-wrapped and loaded onto trucks for distribution to markets around the world. Temperature-controlled logistics ensure that the chocolate remains in perfect condition during transit. Throughout the entire manufacturing process, Toblerone maintains strict quality control measures. Each batch undergoes laboratory testing, including texture analysis, microbial screening, and taste assessments conducted by trained specialists. Data is continuously logged in automated tracking systems, allowing for full traceability of every Toblerone bar produced. Different Toblerone manufacturing facilities may employ slight variations in processing techniques depending on regional ingredient availability and market preferences. Specialty editions, such as Toblerone White Chocolate or Toblerone Dark, require slight modifications in ingredient formulations and processing steps. As consumer preferences evolve, Toblerone continues to innovate while maintaining the brand's heritage of Swiss chocolate craftsmanship. Investments in sustainable cocoa sourcing, eco-friendly packaging solutions, and advanced automation ensure that Toblerone remains a global favorite while reducing its environmental footprint. Through precision engineering, time-honored techniques, and a commitment to quality, every Toblerone bar delivers the signature taste and texture that chocolate lovers around the world cherish. The production of Snickers, one of the world's most popular chocolate bars, is a highly automated and meticulously controlled process designed for efficiency, consistency, and large-scale output. With its signature combination of nougat, caramel, peanuts, and milk chocolate, Snickers is produced in state-of-the-art facilities that use cutting-edge food processing technology, ensuring that every bar meets the brand's high-quality standards. From sourcing the finest raw ingredients to packaging and distribution, every step is optimized to deliver the same taste, texture, and satisfaction in every bite. The journey of a Snickers bar begins with the careful selection of raw materials. The main components include sugar, peanuts, milk powder, cocoa mass, cocoa butter, palm oil, glucose syrup, egg whites, and emulsifiers. These ingredients are sourced from carefully vetted suppliers, ensuring compliance with strict food safety and sustainability standards. Mars, the company behind Snickers, prioritizes responsible ingredient sourcing, ensuring that cocoa is ethically obtained through its Cocoa for Generations program, which promotes fair labor practices and sustainable farming methods. Peanuts, another crucial ingredient, are primarily sourced from the United States, where they are grown under controlled conditions to maintain size, flavor, and crunch. Once the ingredients arrive at the manufacturing facility, they undergo a rigorous quality control process. Each batch is tested for moisture content, purity, and potential contaminants. Peanuts, in particular, go through an additional inspection phase, where they are sorted by size and quality. High-speed optical sorting machines remove any defective or discolored peanuts, ensuring that only the best nuts make it into Snickers bars. The first major step in the Snickers production process is creating the nougat base. Nougat provides the chewy texture that forms the foundation of the bar. It is made by combining sugar, corn syrup, and water, which are heated in large industrial cooking vats to create a syrup. This syrup is then aerated using high-powered whipping machines, which incorporate fine air bubbles, giving the nougat its characteristic light and chewy texture. Egg whites or soy protein are added as stabilizers to help maintain consistency. Once aerated, the nougat is spread onto a moving conveyor belt in a continuous sheet, where it is allowed to cool and set. This process is carefully controlled to prevent the nougat from becoming too hard or too soft. Automated guillotine cutters then slice the nougat sheet into uniform rectangular portions, ensuring that each piece is the exact size required for Snickers bars. Next comes the caramel layer. The caramel in Snickers is made from a blend of sugar, glucose syrup, milk, and butter, which is heated in large stainless steel batch cookers. The temperature is carefully monitored to achieve the perfect viscosity, thick enough to hold its shape, but soft enough to provide a smooth, chewy texture. Once cooked to perfection, the caramel is poured in a controlled stream onto the nougat base. The caramel-covered nougat passes through a cooling tunnel, where it sets just enough to be firm, but still pliable. Now it's time to add the peanuts. Before being incorporated into the bars, the peanuts are roasted in industrial ovens to enhance their flavor and crunch. After roasting, they are cooled and evenly distributed over the caramel layer using precision peanut dispensers. These machines ensure that each bar receives the right amount of peanuts, maintaining uniformity across all Snickers bars. Once the peanuts are in place, the layered nougat, caramel, and peanut sheet moves to the cutting stage. High-speed rotary blades slice the continuous sheet into individual bar-sized portions. Each cut must be precise, ensuring that the caramel and nougat layers remain intact while maintaining a consistent size. The next critical step is chocolate enrobing. The milk chocolate coating used for Snickers bars is made from a blend of cocoa mass, cocoa butter, sugar, and milk powder. This mixture is refined and conched in large machines that continuously grind the chocolate to achieve a smooth texture. The chocolate is then tempered, a process that involves controlled heating and cooling to stabilize the cocoa butter crystals. Proper tempering ensures a glossy finish and prevents fat bloom, which can cause chocolate to develop a dull appearance. At the enrobing station, the cut bars pass through a waterfall of liquid milk chocolate, fully coating them. Excess chocolate is removed using controlled air jets and vibrating conveyors, ensuring an even layer without excessive buildup. Some factories use a two-stage enrobing process, where a thin base coat of chocolate is applied first to create a stable foundation before the final. Thicker chocolate layer is added. After enrobing, the bars enter a multi-zone cooling tunnel. This tunnel gradually lowers the temperature in controlled stages, allowing the chocolate to set properly without developing cracks or dull spots. Once fully cooled, the Snickers bars emerge with a perfectly solidified chocolate coating, ready for quality inspection. Quality control is a critical component of Snickers production. Each bar undergoes a series of automated inspections to ensure that it meets strict specifications. High-speed vision inspection systems equipped with high-resolution cameras scan each bar for defects such as uneven coating, improper size, or misshapen layers. Any bars that do not meet the required standards are automatically rejected and sent for reprocessing. Additional quality checks include weight verification, moisture content analysis, and sensory testing conducted by trained specialists. Once the bars have passed inspection, they move to the packaging stage. Snickers bars are individually wrapped in plastic film using high-speed horizontal flow wrapping machines. These machines use heat sealing technology to create airtight packaging that preserves freshness and prevents contamination. The wrapped bars are then grouped into multi-packs and packed into branded cartons using automated case packers. The final step in the process is palletization and distribution. Automated systems stack the packaged cartons onto pallets in precise formations, optimizing space for transport. These pallets are then shrink-wrapped for stability and loaded onto temperature-controlled trucks for distribution to retailers worldwide. Snickers bars are shipped to over 70 countries, requiring an advanced logistics network to ensure that they arrive fresh and in perfect condition. Throughout the entire production process, Mars maintains stringent food safety and sustainability practices. Each batch undergoes extensive laboratory testing, including microbiological screening, allergen testing, and texture verification. The company also invests in sustainable ingredient sourcing, reducing its environmental footprint through energy-efficient manufacturing processes and eco-friendly packaging solutions. Different Snickers manufacturing facilities may employ slight variations in processing techniques based on regional ingredient availability and consumer preferences. For example, some regions may use alternative chocolate blends with varying cocoa content, while others may modify the nougat or caramel consistency based on market demands. Additionally, special edition Snickers bars, such as Snickers almond or Snickers peanut butter, require modifications in ingredient formulation and production methods. As consumer preferences evolve, Mars continues to innovate while maintaining the classic Snickers taste and texture. Advancements in automation, AI-driven quality control, and sustainable manufacturing practices are shaping the future of Snickers production. Despite these innovations, the fundamental principles of precision, consistency, and quality remain unchanged, ensuring that every Snickers bar delivers the same delicious combination of chewy nougat, gooey caramel, crunchy peanuts, and smooth milk chocolate that has made it a favorite among chocolate lovers worldwide. The production of Tony's Chocolonely chocolate bars is a carefully designed process that emphasizes ethical sourcing, sustainability, and high-quality chocolate-making techniques. Unlike traditional chocolate brands, Tony's Chocolonely is dedicated to creating a slave-free chocolate industry, ensuring that every step in the supply chain is transparent and fair. From sourcing cocoa beans from cooperatives in West Africa to molding and packaging the final bars, the production process is a seamless blend of traditional craftsmanship and modern automation. The journey of a Tony's Chocolonely bar begins with cocoa sourcing. The company partners with cooperatives in Ghana and Côte d'Ivoire, regions that are known for cocoa production, but also face significant challenges related to child labour and unfair wages. Tony's Chocolonely implements direct trade practices, paying a premium for cocoa and providing additional support to farmers through training programs and financial resources. This ensures that the beans are ethically sourced while maintaining a high standard of quality. Once harvested, the cocoa beans go through a meticulous post-harvest process. Farmers ferment the beans for several days, a crucial step that develops the deep, complex flavors needed for premium chocolate. After fermentation, the beans are spread out under the sun to dry, reducing moisture content and preventing mold growth. When dried to the appropriate level, the beans are packed into jute sacks and shipped to Tony's Chocolonely's processing facilities. Upon arrival at the factory, the beans undergo rigorous quality control checks. Samples from each shipment are tested for moisture levels, flavor consistency, and potential contaminants. Beans that pass inspection are stored in climate-controlled silos to maintain freshness before entering the production line. The first step in the chocolate-making process is roasting. Large industrial roasting machines heat the beans at precise temperatures, usually between 120 to 150 degrees Celsius, 248 to 302 degrees Fahrenheit. This process enhances the natural chocolate flavors and eliminates unwanted bitterness. The roasting time and temperature depend on the type of chocolate being produced. Dark chocolate requires a slightly longer roasting process than milk chocolate to develop its rich, bold flavors. Once roasted, the beans enter the winnowing process. A specialized machine cracks open the roasted beans and removes the outer husks, leaving behind the valuable cocoa nibs. These nibs contain both cocoa solids and cocoa butter, the essential components of chocolate. The nibs are then ground into a thick, smooth paste known as chocolate liquor. This process, carried out by industrial grinders, reduces the particle size of the nibs, creating a velvety consistency. At this stage, different chocolate variations begin to take shape. For Tony's Chocolonely's milk chocolate bars, the chocolate liquor is combined with sugar, milk powder, and additional cocoa butter to create a creamy texture. For dark chocolate, higher cocoa percentages are used with less sugar and no milk. The next step in the process is refining. The chocolate mixture is passed through heavy-duty steel rollers that grind the ingredients into ultra-fine particles. This step is crucial for achieving the smooth texture that defines high-quality chocolate. The finer the particles, the better the melt-in-your-mouth experience. Following refining, the chocolate undergoes conching, a process that enhances both texture and flavor. Large conching machines continuously mix and aerate the chocolate for several hours, allowing any residual acidity to evaporate while intensifying the chocolate's richness. The conching time varies depending on the desired flavor profile. Longer conching results in a smoother, more developed taste. After conching, the chocolate is tempered, a precise heating and cooling process that stabilizes the cocoa butter crystals. Proper tempering ensures that Tony's Chocolonely bars have a glossy finish, a satisfying snap when broken, and a long shelf life without developing fat bloom, the white streaks that can appear on improperly tempered chocolate. Once tempered, the liquid chocolate is ready for molding. Unlike most chocolate bars, Tony's Chocolonely bars are intentionally molded in an uneven pattern, symbolizing the unequal distribution of wealth in the chocolate industry. Automated machines pour precise amounts of chocolate into these custom-designed molds, which are then gently vibrated to remove air bubbles and ensure even distribution. The molds are then transferred to a cooling tunnel, where the chocolate gradually solidifies under controlled temperatures. This process prevents the bars from developing surface defects and ensures that they retain their perfect shape. Once the chocolate has fully set, the bars are ejected from the molds and sent to the quality control station. High-speed vision inspection systems scan each bar for defects, such as air bubbles, improper molding, or uneven texture. Any bars that do not meet the required standards are removed from the production line and either reprocessed or discarded. After passing quality checks, the bars move to the packaging stage. Tony's Chocolonely uses brightly colored, easily recognizable wrappers, each featuring bold typography and branding. The packaging process is fully automated, with high-speed wrapping machines, sealing each bar in foil and paper to protect it from moisture and contamination. The wrapped bars are then packed into cartons using robotic case packers. The final step in the process is palletization and distribution. Automated robotic systems stack the packaged bars onto pallets in a precise arrangement, optimizing space for transport. The industrial processing of honey begins not within the walls of the factory, but at the apiaries, where honeybees forage, collect nectar, and begin the complex enzymatic process of transforming floral sugars into the thick, golden liquid we know as honey. Factory-scale honey production starts with the careful coordination between contracted beekeepers and processing plants, which work together to supply bulk honey at a scale large enough to support mass distribution. The first step in the factory process involves the reception and inspection of raw honey as it arrives from the beekeepers' extraction sites. Raw honey is typically delivered in large food-grade steel drums or plastic totes, each capable of holding hundreds of pounds of honey. These containers arrive sealed, labeled with origin data, floral source if known, and batch tracking codes. Upon arrival at the honey processing facility, each container is unloaded onto the receiving dock, where a team of technicians begins the initial quality assurance process. This is far more than a visual check. Industrial honey processors must guarantee that the incoming product is pure, unadulterated, and meets strict legal and food safety standards. The drums are first sampled using a specialized honey sampling spear, a long stainless steel tube designed to pierce through the viscous mass and extract a vertical core from top to bottom. This is essential because honey can stratify, with moisture content, color, and crystallization levels varying from top to bottom. The extracted sample is then homogenized and sent to the quality control laboratory. Here, a battery of tests is performed. Moisture content is measured using refractometers, which determine how much water is present in the honey. Legal standards require honey to contain no more than 20% moisture to prevent fermentation. Beyond moisture testing, analysts perform pollen analysis to verify floral sources and geographic origin, which is important for regulatory labeling and for upholding claims like clover honey or orange blossom honey. Additional tests, such as electrical conductivity, help differentiate between nectar and honeydew honeys, while HMF levels, or hydroxymethylfurfural, are checked to ensure the honey hasn't been exposed to excessive heat during prior storage or transit. High-performance liquid chromatography may also be used to detect the presence of added sugars, which would indicate adulteration and result in immediate rejection of the batch. Once a drum passes inspection and is approved for processing, it is moved to the uncrystallization station. Raw honey can crystallize over time, particularly when stored in cooler environments or when the floral source is rich in glucose. Crystallized or partially crystallized honey must be re-liquefied before it can be filtered or blended. This is achieved by placing the drums in heated chambers or warm water baths, known as hot rooms, where they are gently warmed to temperatures around 95 to 110 degrees Fahrenheit. This temperature range is sufficient to melt crystals without degrading the honey's delicate aromatic and enzymatic properties. Large facilities often use drum heating tunnels that can accommodate dozens of drums at a time. These tunnels employ radiant heat panels and convection fans that maintain a steady, uniform temperature throughout the enclosure. Temperature probes are inserted into each drum to ensure that internal temperatures rise slowly and evenly, preventing localized overheating which could darken the honey or degrade its quality. This gentle warming process can take anywhere from 24 to 72 hours, depending on the degree of crystallization and the initial temperature of the honey when it arrived. Now it's time to go into the liquefaction and transfer stage, where the now softened honey is pumped out of the drums and into the factory's primary processing line. This step requires specialized food-grade pumps capable of handling thick, sticky materials without introducing air bubbles or damaging the honey's texture. Positive displacement pumps, such as rotary lobe or progressive cavity pumps, are commonly used for this purpose. These pumps are designed to move viscous fluids at a steady rate without causing foaming or aeration, which can negatively impact downstream processing. As the honey is pumped from each drum, it passes through heated stainless steel pipelines that maintain a consistent temperature, usually around 110 to 120 degrees Fahrenheit, to keep the honey fluid during transit. The pipelines are insulated to minimize heat loss, and the entire system is cleaned between batches using CIP or clean-in-place systems, which circulate hot water and food-safe cleaning agents to maintain sanitary conditions. Valves and flow meters are used to control how much honey enters the next phase, which is usually a settling or holding tank. These tanks are large vertical silos equipped with gentle agitation paddles to keep the honey uniform without whipping air into it. At this stage, the honey is allowed to rest briefly, giving suspended particles like wax fragments, bee parts, or pollen clumps time to rise or settle. Some facilities incorporate slow-flow decanting chambers or skimming belts that remove surface foam and floating debris. The goal here is to prepare the honey for the critical filtration stage without exposing it to excessive agitation or temperature shifts, which could compromise quality. But up next is the filtration stage, one of the most technically controlled steps in factory honey processing. The challenge with filtering honey lies in removing impurities while preserving beneficial properties such as flavor, aroma, and trace pollen content. To accomplish this, processors use a series of progressively finer filters, starting with coarse metal mesh screens and moving to finer, micron-level filtration pads or cartridges. Initially, the honey flows through vibratory sieve filters or centrifugal strainers that remove large debris, including chunks of wax or bee remnants. These are often equipped with auto-cleaning screens that rotate or vibrate to prevent clogging. After coarse filtering, the honey enters a fine filtration system. Depth filters composed of cellulose or food-grade polypropylene are commonly used. These filters remove particles as small as 5 to 10 microns, including residual wax, dust, and crystallized sugar particles that could initiate recrystallization in the final product. To aid this process, the honey is maintained at a precise temperature of about 120 to 130 degrees Fahrenheit. warm enough to reduce viscosity and improve flow through filters, but not so hot as to destroy heat-sensitive enzymes or antioxidants. Inline temperature sensors and automated control panels ensure that every gallon of honey is processed under identical thermal conditions. Some advanced facilities even use vacuum-assisted filtration to further reduce the need for high temperatures, thereby preserving more of the honey's raw characteristics. Once filtration is complete, the honey is collected in large stainless steel blending tanks. These tanks are used to homogenize different batches of honey, standardize flavor profiles, and adjust final parameters such as color and clarity. Mixing paddles rotate at slow, controlled speeds to avoid aeration while ensuring a uniform blend. It's at this stage that some producers may add trace amounts of previously tested and approved batches to maintain flavor consistency across large volumes, especially if multiple floral sources are involved. Now it's time to explore the homogenization process in more detail, as this step plays a pivotal role in ensuring that every bottle or jar of honey pulled from the line is virtually identical in texture, color, and taste. Honey, being a natural product, can vary widely between batches due to differences in nectar sources, collection times, and even seasonal variations. To manage these inconsistencies, processors rely on computer-controlled blending protocols that match incoming honey against established reference standards. Before blending begins, technicians perform sensory and analytical testing on the batch, including color measurement using the Fund scale, which classifies honey from water white to dark amber. Flavor notes are assessed by trained sensory panels or electronic nose devices, while moisture and acidity levels are verified to determine blending ratios. If a batch is slightly darker than the standard product line, a portion of lighter honey is added to balance the color. If a batch is too viscous, a blend with a slightly higher moisture content is introduced to bring the final viscosity within specification. Mixing tanks used in this process are often jacketed with warm water or glycol to maintain the blending temperature at a steady 110 to 120 degrees Fahrenheit. Internal baffles guide the flow of honey, ensuring thorough integration without the formation of dead zones or stratification. The tanks are usually equipped with inline sensors that continuously monitor parameters like Brix, viscosity, and turbidity. The blending cycle may take several hours for large volumes, and throughout the process, automated samplers pull small amounts at regular intervals to verify that the blend remains within quality parameters. Once homogenization is complete, the honey is transferred to the final holding tanks that feed directly into the packaging lines. These tanks are placed on load cells that precisely measure the volume of honey dispensed into each container. From this point forward, the product must move through sealed, temperature-controlled systems to ensure no contamination occurs before bottling. And that leads directly into the highly synchronized packaging phase. As the homogenized honey flows from the final holding tanks into the packaging system, the entire process becomes a high-speed, tightly orchestrated sequence of mechanical precision and hygiene control. This stage is where the product begins to take on its final consumer-facing form, whether it's packaged in squeeze bottles, glass jars, tubs, or bulk containers. The packaging line starts with the selection and preparation of containers, which are fed into the system from large hopper units or depalletizers, depending on the container type. Plastic bottles often arrive pre-formed and stacked in bulk, while glass jars may come in pallets wrapped in protective plastic film. Regardless of material, every container goes through a rigorous cleaning phase before it is allowed anywhere near the honey. The first step in container preparation is an air rinse or ionized air cleaning process. Each container is inverted and passed through a chamber where blasts of filtered, pressurized air are directed inside. Ionized air is used specifically to neutralize any static charges that might cause dust or particles to cling to the sides of the container. In glass packaging lines, this process may be supplemented with a vacuum extractor that removes dislodged particles immediately after the air rinse. Some facilities also opt for a UV light exposure chamber that the containers pass through as an added antimicrobial safeguard. All of these steps are executed on automated conveyor systems, synchronized to keep pace with the fill line. Now it's time to go into the filling stage, which must be executed with extreme accuracy to ensure every package contains the correct weight or volume of honey. Honey's thick, slow-moving consistency makes it a challenging product to fill efficiently at scale. To meet this challenge, factories use volumetric piston fillers or gear pump filling machines, both of which are well suited for handling viscous, sticky products. These machines are equipped with heated nozzles and jacketed tubing to maintain the honey at an optimal temperature, typically around 110 degrees Fahrenheit, so it flows smoothly without foaming or dribbling. Each filling station is designed with multiple nozzles, often ranging from 4 to 16, depending on the line's speed and scale. The nozzles are programmed to descend into the containers during filling and retract as the level rises, a method known as bottom-up filling. This minimizes splashing and helps prevent the introduction of air bubbles, which can interfere with the product's shelf stability and aesthetic appearance. Inline check weighers are stationed just downstream of the filling heads, automatically rejecting any underfilled or overfilled containers from the line. Any deviation outside a narrow tolerance window triggers an immediate alert and mechanical removal. Immediately after filling, the containers are transferred to the capping and sealing station. For plastic bottles, this often involves a torque-controlled capper that applies precise rotational force to ensure a tight but not damaging seal. Flip-top caps, disc-top caps, or screw caps are automatically sorted and fed into place using vibratory feeders and cap chutes. In the case of glass jars, the capping process may involve steam vacuum sealing with metal lids, creating a hermetic seal that ensures freshness and shelf stability. As the lid is applied, a puff of steam is injected into the headspace, which condenses and creates a partial vacuum as the jar cools. Some packaging lines also include an induction sealing station. This involves placing a foil liner inside the cap, which is then sealed to the lip of the container using electromagnetic induction to heat and bond the foil to the rim. This creates a tamper-evident barrier that reassures consumers while also acting as an additional contamination safeguard. Once sealed, the containers pass through a water or air rinse to remove any stray honey drips from the filling station, followed by a drying tunnel that uses forced warm air to eliminate surface moisture before labeling. But up next is the labeling and coding process, where the honey finally begins to take on its retail-ready appearance. Labeling machines apply product labels at high speed using pressure-sensitive or shrink-sleeve labels, depending on the packaging format. Pressure-sensitive labels are peeled from a backing roll and applied to the container with rollers, while shrink-sleeve labels are wrapped around the container and heat-shrunk into place using a steam tunnel. Each label is applied with extreme precision using optical sensors that detect the exact placement zone, ensuring uniformity across all units. At this point, the line integrates the critical traceability step, date coding, and batch identification. Inkjet or laser coders are installed directly after the labeling station and are configured to print the production date, batch number, and expiration date onto the label, cap, or bottleneck. These codes are essential for tracking product back to its source in the event of a recall or quality issue, and they also help with inventory rotation throughout the supply chain. Vision systems verify the presence and legibility of these codes, and any container missing its code is automatically rejected from the line. Once labeled and coded, the honey containers move toward the secondary packaging phase. Here, They are grouped based on retail configuration, single bottles, multi-packs, or cartons, and loaded into larger corrugated cardboard cases. Robotic case packers or drop pack mechanisms handle this process with extreme care, particularly with glass containers, which require dividers and cushioning. Once the cases are assembled and filled, they're sealed using hot melt glue or tape and then passed through a check weigher to verify package weight consistency. The final stage in the packaging process is palletization, where filled cases are stacked in precise formations onto wooden or plastic pallets. Robotic palletizers equipped with vacuum grippers or mechanical arms lift and arrange the cases row by row, ensuring that weight is evenly distributed to prevent collapse during transport. Once the pallet is complete, it is wrapped with industrial stretch film to stabilize the load and protect it from moisture and dust. Each pallet receives a barcode label containing all relevant shipping and traceability data, including product type, quantity, destination, and handling instructions. Now it's time to go into the warehousing and distribution stage, which is vital to maintaining honey's shelf life and ensuring that product quality is preserved from the factory to the consumer. Honey is hygroscopic, meaning it absorbs moisture from the air, so warehousing conditions must be carefully controlled. Finished pallets are moved to temperature and humidity controlled warehouse zones where the ambient environment is kept between 60 and 75 degrees Fahrenheit, with relative humidity below 60% to prevent moisture ingress that could lead to fermentation or spoilage. Inventory is managed using a warehouse management system that assigns each pallet a digital location code, tracks product age, and ensures first in, first out rotation. Automated guided vehicles or forklifts retrieve pallets based on shipping schedules, and every movement is recorded in a centralized database. This allows full traceability not just back to the packaging date, but all the way through, blending batches and raw honey origins. If a quality issue were ever discovered post-shipment, the manufacturer could instantly identify and recall only the affected lot numbers. Before pallets leave the facility, they may undergo one final inspection. Logistics personnel verify that labels match the shipping documentation, confirm temperature logs for any time-sensitive products, and ensure that stretch wrapping and labeling meet the receiving distributor's requirements. Some retailers have specific palletization rules, like maximum stack height or barcode placement, that must be followed exactly to avoid supply chain disruptions. Once cleared, pallets are loaded into temperature-controlled trucks using dock levelers that ensure a smooth transition from warehouse to vehicle. These trucks are often equipped with sensors that track internal temperature and humidity levels during transit. If any threshold is breached during transportation, alerts are sent to the distribution center to allow preventive action. This step is critical because improper handling during shipping can undo months of careful processing. For instance, exposure to excessive heat can darken the honey, degrade its enzymes, and even trigger fermentation if the moisture content is borderline. As the honey moves through regional distribution centers and into retail outlets, it remains in sealed containers that shield it from light and air. Most honey has a shelf life of 2 years or more if stored properly, thanks to its low water activity and high sugar concentration, which naturally inhibit microbial growth. However, the quality and freshness perceived by the consumer are still closely tied to how well every part of the manufacturing and distribution process has been executed, from the bee to the bottle to the shelf. Every detail, every degree of heat, every micron of filtration, and every second of line timing plays a role in preserving the integrity of the final product. And even after it reaches store shelves, the story of how honey is made in a factory continues to resonate with precision, craftsmanship, and scientific control. To fully understand the industrial production of honey, it's important to go beyond the mechanics and explore the subtleties of product customization regulatory compliance, and the final quality control processes that make factory-scale honey not just uniform, but legally marketable and consumer safe. After the honey has been packaged, palletized, and staged for distribution, another dimension of the process becomes active: the post-packaging quality assurance system. This system acts as a final safeguard to confirm that the product leaving the facility not only meets internal quality standards, but also complies with local, national, and international food safety laws. One of the most essential tasks during this final phase is the detailed sampling and archiving of batch samples. From each production lot, designated containers are pulled from the finished goods and sent to the factory's on-site analytical laboratory. These samples are catalogued, sealed, and retained in climate-controlled archives for up to several years, depending on regulatory requirements. This ensures that if a complaint, audit, or issue ever arises, the facility can test the retained sample and compare it to the current product in question. The archive system is tied directly into the facility's digital traceability records, allowing a sample to be matched instantly to the exact floral source. Filtration parameters, blend ratios, packaging date, and even which employee signed off on the batch. Parallel to this, comprehensive chemical and microbiological testing is performed on the pooled samples. Even though honey is naturally resistant to microbial growth due to its low water activity and high sugar content, every lot is still tested for yeast, mold, and spore-forming bacteria, such as Clostridium botulinum. The latter is especially critical for honey intended for infant consumption. Though honey is generally not recommended for children under 1 year of age, advanced polymerase chain reaction methods and microbial plating techniques are used in-house or sent to certified third-party labs for verification. The chemical testing regimen goes even deeper. In addition to previously mentioned standards such as moisture and HMF, tests are conducted to confirm that no contaminants have been introduced during packaging. This includes screenings for bisphenol A in plastic containers, phthalates, heavy metals like lead or arsenic, and residues from cleaning agents. Food-grade lubricants used in machinery are also tightly controlled to prevent incidental contact, and testing verifies their absence in finished products. Random bottles are sometimes subject to full shelf life simulation testing, where accelerated aging is used to project how the honey will behave under various conditions over time. Now it's time to go into the regulatory labeling and export compliance procedures, a crucial and often complex step for companies that ship honey across borders. Labeling is governed by a mixture of national food laws and international trade agreements. In the United States, for example, the Food and Drug Administration requires that honey be labeled with the common or usual name, net weight, ingredient list, the name and place of the business, and nutrition facts. Additional designations such as raw, organic, unfiltered, or wildflower must be substantiated with supply chain documentation and laboratory verification. For export to the European Union, labeling rules become even more intricate. The EU requires origin declarations if more than one country of origin is involved, meaning that a blend containing honey from, for example, Argentina and Canada must say, blend of honeys from more than one country, unless the exact percentages are broken down. Pollen analysis and isotopic testing are commonly used to verify the authenticity and origin of honey destined for the EU, and the entire production process must comply with the European Honey Directive. This includes ensuring that no heat treatment exceeds 40 degrees Celsius if the product is labeled as raw, and that no enzymatic activity is lost. The labeling department works in tandem with regulatory and export compliance officers, who maintain up-to-date databases of international standards, customs documentation, and product certifications. These certifications may include organic certificates, non-GMO verification, halal or kosher certification, fair trade documentation, and country-specific certifications of analysis. Every pallet destined for export is linked to a detailed manifest, and random audits ensure that the physical label matches its digital record in the product lifecycle database. Any discrepancy can halt a shipment and trigger a full traceability review. But up next is the specialization phase, where some facilities go beyond traditional honey and produce value-added variations to meet niche markets or changing consumer demands. This might include whipped or creamed honey, honey infused with natural flavors or botanical extracts, or honey blended with additives like royal jelly, bee pollen, or propolis. Each of these variations requires separate processing lines or batch scheduling to avoid cross-contamination and to comply with labeling laws that distinguish these products from standard filtered honey. Creamed honey, for example, requires controlled crystallization to achieve a smooth, spreadable texture. After filtration and homogenization, the honey is seeded with a small amount of finely crystallized honey and slowly stirred under cool temperatures in a creaming tank. This controlled environment allows microcrystals to form uniformly, resulting in a product that remains spreadable even when stored at room temperature. The tanks used in this process are jacketed with cooling fluid and fitted with slow-turning paddles that prevent the formation of large crystals. Flavored honey follows a different path. Natural flavor compounds, such as cinnamon, ginger, vanilla, lemon, or even chili, are emulsified into a small portion of honey before being slowly blended into the main batch. This ensures even distribution and prevents hotspots of flavor. Each additive must be food safe, approved by regulatory bodies, and tested for interaction with honey's enzymes and acidity. In some cases, additional filtration or viscosity adjustment is needed to maintain the same flow behavior in the bottling equipment. These specialty honeys are typically packaged in smaller volumes and targeted toward gourmet or health-conscious consumers.